Please subscribe to support the channel. There's a secret star in our universe that doesn't play by the rules. Astronomers expected the cosmos to behave in a certain way, that the earliest stars would follow the predictions of the Big Bang Theory, and that their descendants would all line up neatly with those cosmic expectations. But then came a discovery that sent shockwaves through astronomy. A single star, small and faint, sitting quietly in the constellation of Leo, yet challenging one of the most fundamental ideas about how the universe began. This strange object is known as Caffau's star, and it's been described as a cosmic troublemaker, a relic that shouldn't exist if our theories are correct. It seems to break the rules of the Big Bang, or at the very least, expose cracks in our understanding of how the first stars formed. The very existence of Caffau's star forces us to ask uncomfortable questions. Could it mean the Big Bang Theory is incomplete? Could it represent a loophole in the cosmic rulebook? Or could it be whispering to us about hidden physics we haven't discovered yet? These are not small questions. They cut to the heart of how the universe came to be, how galaxies evolved, and even how we came to exist. In this essay, we're going to explore this mystery in depth, breaking it down piece by piece so you can see why this one humble star has caused such an uproar in the scientific community. Most people, when they hear the words Big Bang Theory, imagine the beginning of everything as an explosive moment, a gigantic burst of energy, light, and matter that set the cosmos into motion. It's often visualized as if it were a bomb going off in an empty void, scattering stars and galaxies everywhere. But the actual scientific picture is more nuanced and, in many ways, far stranger. The Big Bang wasn't an explosion in space, it was the expansion of space itself. Time, matter, and the laws of physics as we know them came into existence in that initial moment nearly 13.8 billion years ago. This grand idea, the Big Bang Theory, doesn't just serve as a poetic explanation for the universe's origins, it provides predictions. It's a theory that has been tested against countless observations, from the distribution of galaxies to the afterglow of the Big Bang itself, known as the cosmic microwave background radiation. One of the key things it predicts is the composition of the very first matter and, consequently, the nature of the very first stars. To set the scene properly, let's imagine the early universe not as an empty stage, but as one flooded with the simplest building blocks of matter. Within the first few minutes after the Big Bang, a process called Big Bang nucleosynthesis occurred. In those fleeting moments, the extreme heat and density allowed protons and neutrons to fuse, creating the first atomic nuclei. But because the universe cooled rapidly, the process was brief and limited. The result was a cosmos dominated by hydrogen, about 75% by mass, and helium, about 25%, with just a whisper of lithium and beryllium. Heavier elements, the stuff that makes planets, life, and even our blood, did not exist yet. So when we talk about the first stars, we're talking about objects that had to form in a universe made almost entirely of these lightest elements. No carbon, no oxygen, no nitrogen, no iron. In astronomy, all of those heavier elements are collectively referred to as metals. And here's where the predictions get interesting. Without metals, the physics of star formation changes dramatically. You see, metals play a critical role in how gas clouds cool and collapse under gravity. In today's universe, when a cloud of gas starts to collapse to form a star, heavy elements radiate away energy, allowing the gas to cool and fragment into smaller pieces. This process makes it possible to form stars of many different sizes, including small, long-lived stars like our Sun. But in a metal-free universe, cooling would be far less efficient. Astronomers reasoned that the earliest star-forming clouds couldn't fragment into many small pieces. Instead, they would collapse into a few very large clumps, giving rise to massive stars, stars that might be 100 or even 200 times more massive than the Sun. Massive stars burn hot and fast. They exhaust their nuclear fuel in only a few million years before exploding as supernovae. So the prediction was clear. The first generation of stars, sometimes called population 3 stars, would be enormous, unstable, and ephemeral. They would live fast, die young, and enrich the universe with heavier elements for the first time. This process would pave the way for the next generations of stars, which would then contain those new metals, cooling more efficiently, and forming smaller, more diverse stellar populations. For decades, this story was the accepted narrative of cosmic history. It fit neatly into the Big Bang framework. It explained why we see the periodic table we have today, why galaxies look the way they do, and even why planets like Earth exist. The timeline was clean. Big Bang, hydrogen and helium, giant population 3 stars, supernova explosions, enriched gas clouds, second-generation stars, galaxies, solar systems, and life. So, if we zoom out and look at this sequence from the perspective of a scientist in the late 20th century, the expectations were straightforward. You wouldn't expect to find any long-lived small stars from the earliest generation. They simply weren't supposed to exist. By the time we get to stars like the Sun, with its carbon, nitrogen, oxygen, and other metals, we're already many stellar generations into the universe's history. But here's the crucial thing. This elegant story leaves no room for anomalies like Caffau's star. According to theory, no low-mass, nearly metal-free stars should have survived to the present day. The predictions were so strong, in fact, that for decades astronomers didn't even really look for them. They assumed such stars would be impossible. Instead, they searched for indirect signs of population 3 stars by studying ancient galaxies, supernova remnants, and the metallicity of old stars. And yet, against all odds, telescopes would eventually stumble upon something unexpected. A star whose very existence seems to whisper, "Your story of the universe might be incomplete." Caffau's star doesn't align with these tidy predictions. It's not massive, it's not short-lived, and it's not enriched with metals in the way theory demands. It's a quiet, long-lived, low-mass star, and according to everything we just laid out, it should never have been able to form. That's why setting the scene with the standard Big Bang prediction is so important. Because without understanding the expectations, you can't fully appreciate just how shocking it was to find a star that refuses to obey them. It's the cosmic equivalent of writing a script for how the universe's first act should unfold, and then discovering a character on stage who isn't supposed to be in the play at all. Alright, let's slow down and carefully unfold the timeline, because this is where the entire puzzle of Caffau's star begins to take shape. When we talk about the aftermath of the Big Bang, it's easy to imagine it as a single moment in time, but in reality, it was a sequence of cosmic epochs, each one lasting different amounts of time, each with its own rules and physical processes, and each building on the last. To understand why Caffau's star is so strange, we have to walk through those early stages step by step. The Big Bang itself, the literal beginning, occurred about 13.8 billion years ago. At the very instant of creation, the universe was unimaginably hot, dense, and filled with energy. Matter, as we know it, didn't exist yet. Instead, the cosmos was a seething plasma of fundamental particles: quarks, gluons, electrons, neutrinos, and photons, all buzzing around in a chaotic soup. This earliest phase lasted only fractions of a second, but during that time, forces and particles that define our reality began to separate out. Gravity, electromagnetism, and the nuclear forces each established their domains, and particles like protons and neutrons came into being. Within the first few minutes, the temperature of the universe dropped enough for something remarkable to happen. Protons and neutrons began sticking together, forming the very first atomic nuclei. This process is called Big Bang nucleosynthesis, and it lasted for only about 20 minutes. During this brief window, the universe was essentially acting as a giant nuclear reactor, fusing simple particles into the lightest elements. But because it cooled so quickly, the nuclear reactions couldn't go very far. The heavy elements we know today, like carbon, oxygen, silicon, or iron, couldn't form under those conditions. Only the lightest ones could be forged. The end result was a universe that consisted of about 75% hydrogen and 25% helium by mass, with only a tiny trace of lithium and beryllium. To put that in perspective, if you could scoop up a bucket of matter from the universe at that time, nearly every atom inside it would be hydrogen, and nearly all the rest would be helium. You wouldn't find carbon. You wouldn't find oxygen. You wouldn't find iron. None of the things we take for granted on Earth, the oxygen we breathe, the calcium in our bones, the silicon in rocks, the iron in your blood, were present in those first moments. They had to come later. So what did the universe look like at this stage? Imagine a vast, expanding ocean of hydrogen and helium gas, smooth and nearly uniform, stretching in every direction. For the first few 100,000 years, this gas was so hot that electrons couldn't bind to nuclei. Photons, particles of light, were constantly colliding with charged particles, scattering in all directions, making the universe opaque, like the inside of a glowing furnace. Then, about 380,000 years after the Big Bang, the universe cooled enough for electrons to settle into stable orbits around nuclei. This event, called recombination, gave birth to the first true atoms. For the first time, light could travel freely through space without constant scattering. That ancient light is what we now see as the cosmic microwave background, a kind of baby picture of the universe frozen in time. But even though the fog cleared and light could finally stream across the cosmos, the universe was still dark in another sense. There were no stars yet, no galaxies, no planets. Just vast clouds of neutral hydrogen and helium atoms drifting through space. This period, sometimes called the Cosmic Dark Ages, lasted for hundreds of millions of years. Gravity slowly began to gather matter into denser regions, but the process was slow. Without heavier elements to help the gas cool and collapse efficiently, star formation took much longer to get underway. It's here, in this dark, metal-free universe, that the theoretical population 3 stars were supposed to appear. According to models, the first gravitationally bound clumps of hydrogen and helium eventually grew dense enough for nuclear fusion to ignite, giving birth to the very first stars. And because there were no metals to aid in cooling, these stars should have been extremely massive. They would shine brilliantly for a short time and then explode, seeding the universe with the very first heavier elements. The timeline up to this point is clean and, for the most part, confirmed by observation. We can measure the abundance of hydrogen, helium, and lithium in the universe today, and they match the predictions of Big Bang nucleosynthesis very closely, with one nagging exception: lithium. The theory predicts a certain amount of lithium should exist, but when astronomers look at ancient stars, they consistently find less than expected. This lithium problem is already a clue that something about the timeline may be more complicated than we think. Keep that in mind, because Caffau's star takes this problem and amplifies it to a new level. So, to clarify the timeline. A first few minutes, Big Bang nucleosynthesis produces hydrogen, helium, and a tiny trace of lithium. A first 380,000 years. Universe remains a hot plasma until recombination, when atoms finally form and light can travel freely. A cosmic dark ages. For hundreds of millions of years, the universe is filled with neutral hydrogen and helium, with no stars or galaxies yet. Our first stars ignite. Gravity eventually triggers star formation, leading to massive population 3 stars that enrich the cosmos with heavier elements. By the time we arrive at the universe a few 100 million years old, the stage is set for a transformation. Galaxies begin to form. Stars of newer generations appear. Heavy elements start to accumulate. And with those heavy elements comes the possibility of planets, chemistry, and life. But here's the twist: if this sequence is correct, then every star we see today should reflect its place in that cosmic timeline. Ancient stars should still show the fingerprints of those earliest conditions: hydrogen, helium, and traces of lithium, but should also bear evidence of enrichment from the explosions of the first giants. What astronomers never expected was to find a small, long-lived star still existing today that seems to have formed from gas almost as pristine as that of the early universe. And yet, that's exactly what Caffau's star appears to be. Its chemical makeup suggests it formed from gas that had almost no heavy elements, almost as if it skipped the entire enrichment process. It is like a fossil trapped in time, a star that still carries the signature of the universe as it was shortly after the Big Bang. But according to the timeline we just laid out, stars like this should not exist. This is why Caffau's star is so provocative. It forces us to revisit the neat progression of cosmic history. Did the early universe allow small stars to form despite the lack of metals? Did something in the cooling process work differently than we thought? Or is there a missing piece of physics that we simply haven't uncovered yet? Whatever the answer, the timeline of hydrogen, helium, and lithium after the Big Bang is the backdrop against which this cosmic enigma shines, or perhaps more accurately, quietly glows. Let's now turn our focus to the fabled first stars, the ones that cosmologists and astronomers have placed at the very dawn of stellar history. These stars are known as population 3 stars, and they occupy a special place in both theoretical astrophysics and our imagination. They are often described as the universe's first lighthouses, piercing the darkness of the cosmic night for the very first time. But their significance goes far beyond poetry. They represent the crucial link between the pristine universe left behind by the Big Bang and the rich, chemically complex cosmos we inhabit today. To explain why they were expected to be so unusual, let's revisit the basic conditions of the early universe. As we clarified earlier, after the Big Bang, the universe consisted almost entirely of hydrogen and helium, with a faint sprinkling of lithium and beryllium. Heavier elements, which astronomers broadly refer to as metals, were completely absent. And, in the physics of star formation, that detail makes all the difference. When a cloud of gas collapses under its own gravity to form a star, one of the key processes at work is cooling. If the gas can radiate away heat efficiently, it can collapse further, fragment, and form smaller stars. Metals, such as carbon, oxygen, and iron, act as powerful coolants because they can radiate energy through their atomic transitions. Without metals, however, the ability of gas to shed heat is drastically reduced. What does this mean in practical terms? It means that the primordial clouds of hydrogen and helium in the early universe wouldn't have been able to fragment into small clumps the way modern molecular clouds do. Instead, they would have collapsed into much larger, more massive clumps. This led astronomers to predict that population 3 stars would be giants. Not giants in the sense of stars like Betelgeuse, which is large but still part of today's stellar population, but truly massive, titanic objects. Theoretical models suggested they might range anywhere from 30 times the mass of our Sun to perhaps as high as 200 or even 300 solar masses. Imagine a star hundreds of times larger and more luminous than our Sun, burning millions of times brighter. These stars would have been so hot and so violent in their fusion processes that they would live for only a brief cosmic instant, a few million years at most. For comparison, our Sun has a lifespan of about 10 billion years, and it's only halfway through that. A population 3 star would be like a match flame compared to a candle, brilliant, intense, but fleeting. The significance of these stars lies in their role as cosmic forges. Hydrogen and helium, by themselves, cannot build the diversity of elements we find around us. Carbon, nitrogen, oxygen, silicon, and iron. These heavier elements are produced in the cores of stars through nuclear fusion. When stars reach the end of their lives and explode as supernovae, they scatter these elements into the surrounding space, enriching the interstellar medium. This process is often called stellar nucleosynthesis and is the reason why we say, we are made of star stuff. Population 3 stars, then, were expected to be the very first cosmic alchemists. They would take the raw hydrogen and helium left by the Big Bang and fuse it into heavier elements, seeding the universe with the ingredients needed for the next generations of stars, for planets, and eventually for life itself. Without them, the cosmos would still be chemically barren. Every element heavier than helium, including the oxygen in the air you're breathing right now and the calcium in your bones, traces its origin back to stars. Population 3 stars are the beginning of that story. Because of their size and intensity, however, none of these stars were expected to survive to the present day. Their lifespans were far too short. They should all have burned out billions of years ago, leaving only traces of their existence in the chemical makeup of later stars. That's why astronomers have long considered them a lost generation. We can infer that they existed because the universe is chemically enriched, but we don't expect to ever find one still alive. Instead, the search has focused on their descendants, stars from later generations that carry the chemical fingerprints of those first explosions. These are sometimes called population 2 stars, and they tend to have very low metallicity compared to stars like our Sun, a population 1 star. Here's an important detail. Because no population 3 stars have ever been directly observed, everything we know about them comes from theory and computer simulations. Supercomputer models of the early universe simulate the collapse of primordial gas clouds and the ignition of the first stars. These simulations consistently show the same outcome. Massive stars form, they live short lives, and then they explode. Observations of extremely old, metal-poor stars in the Milky Way support this narrative, because the chemical ratios in those stars suggest they were seeded by one or a few supernova explosions from very massive progenitors. And so, for decades, astronomers were confident in this picture. It was neat, it was elegant, and it made sense. No small, metal-free stars should exist today. None. The very physics of star formation forbids it. If you're looking at a small, long-lived star, then by definition it must contain some metals, because without them, the gas cloud couldn't have cooled enough to form such a small star in the first place. But then comes the cosmic rebel, Caffau's star. This faint, seemingly unremarkable star in the constellation Leo refuses to follow the rules. It looks, chemically, like it should belong to the population 3 category. It has almost no metals at all, and yet it's small, faint, and long-lived. In other words, it's precisely the kind of star theory says should be impossible. If Caffau's star really is a relic of the early universe, then the predictions about population 3 stars being exclusively massive and short-lived might need a serious revision. To put it bluntly, population 3 stars were supposed to be the giants of the early universe, brief but transformative. They were not supposed to leave behind small survivors that could still be burning quietly today. And yet, here we are, confronted with a star that seems to contradict that assumption. This is why Caffau's star has attracted so much attention. It isn't just a curiosity. It's a potential crack in the foundation of how we understand the universe's very first generation of stars. It forces us to ask, were the first stars really only massive and short-lived? Or did some of them manage, against all odds, to form as small, long-lived stars, slipping through the cracks of our models and surviving to this day? If the latter is true, then the history of the cosmos is far more complex and far more intriguing than we ever imagined. When astronomers talk about metals, they're not using the word in the same way that we do in everyday life. In astronomy, everything heavier than helium is considered a metal. That means carbon, nitrogen, oxygen, silicon, calcium, iron, even elements like sulfur and phosphorus that we wouldn't normally call metals, all fall under this category. It's a strange quirk of terminology, but it reflects a fundamental truth about the cosmos. Hydrogen and helium dominate the universe, and everything else is rare in comparison. To understand why metals matter so much in stars, and why later generations of stars contain them while the earliest stars did not, we need to look closely at how stars evolve and recycle material back into the universe. Think of the cosmos as a giant cycle of birth, life, and death, with stars acting as both creators and destroyers. Let's begin with the first generation, the population 3 stars we discussed earlier. These massive, metal-free stars formed from the pure hydrogen and helium left behind by the Big Bang. Because they were so large, they burned hot and fast, fusing hydrogen into helium, helium into carbon, and eventually creating heavier elements like oxygen, silicon, and iron in their cores. When these stars reached the ends of their lives, they didn't die quietly. They exploded in violent supernovae, blasting those newly created heavy elements out into the surrounding space. That process, stellar nucleosynthesis combined with supernova enrichment, is what seeded the universe with metals for the very first time. In the aftermath of these explosions, the once pristine hydrogen and helium clouds became laced with traces of carbon, oxygen, nitrogen, and iron. These metals mixed into the interstellar medium, the vast oceans of gas and dust from which new stars are born. This recycling of material is the key reason why later generations of stars contain metals. Every generation of stars contributes a little more to the chemical richness of the universe. Population 2 stars, which formed after the first stars exploded, were born in environments that already contained some metals. Not much, they're still extremely metal-poor compared to our Sun, but enough to make them distinct from the original population 3 giants. Then came population 1 stars, like our Sun, which formed in a universe that had already gone through many cycles of star birth and death, enriching the gas clouds with increasingly higher metallicity. That's why the Sun contains about 2% metals by mass, a seemingly tiny amount, but compared to the early universe's 0, it's a massive difference. So why are metals so important in stars? First, they play a vital role in how stars form in the first place. As I mentioned earlier, metals allow gas clouds to cool more efficiently. When a cloud collapses under gravity, it heats up. To fragment into smaller clumps, the seeds of individual stars, that heat needs to be radiated away. Hydrogen and helium alone aren't good at radiating energy, but metals are. They have complex electron structures that allow them to absorb and emit radiation across a wide range of wavelengths. This cooling mechanism makes it possible for small, long-lived stars to form. Without metals, the clouds stay too hot, collapse into fewer clumps, and give rise to very large stars. That's why the earliest population 3 stars were expected to be massive. Second, metals influence the structure and evolution of stars themselves. Elements like carbon, nitrogen, and oxygen participate in fusion processes, such as the CNO cycle, which dominates energy production in stars more massive than the Sun. Metals also affect how energy moves through a star's interior. Higher metallicity stars tend to have more opaque interiors, which changes how heat is transported and can alter the star's size, temperature, and brightness. Third, metals are essential for everything beyond stars. Planets, for example, require heavy elements to form. A star system with low metallicity is less likely to have rocky planets because there simply aren't enough building blocks like silicon, magnesium, and iron available. Life as we know it also depends on metals. Carbon is the backbone of organic chemistry. Oxygen is essential for respiration. Phosphorus is a key part of DNA, and iron carries oxygen in our blood. Without metals, there could be no chemistry of life. This brings us back to why later generations of stars naturally contain metals. Each cycle of star formation enriches the cosmic medium a little more. A population 2 star might have metallicity as low as 1/10,000th of the Sun's, while a population 1 star like the Sun has much more. As galaxies evolve, metallicity gradually increases, though not uniformly. For example, stars near the center of the Milky Way, where star formation has been especially active, tend to have higher metallicity than stars in the outer halo, which formed earlier and from less enriched material. In this cosmic ladder, metals act like timestamps. By measuring a star's metallicity, astronomers can estimate its age and place in the sequence of stellar generations. Low metallicity suggests great age, because the star formed before the universe had been significantly enriched by earlier generations. High metallicity suggests youth, because the star formed after countless generations of supernovae had spread heavy elements far and wide. This is precisely why Caffau's star is so puzzling. It is one of the most metal-poor stars ever found, which immediately suggests it belongs to the very earliest generations. But unlike the massive population 3 stars predicted by theory, Caffau's star is small, dim, and long-lived. It seems to belong to an age when metals were scarce, so scarce that, according to our understanding, stars of its type should never have formed at all. Its mere existence points to a gap in our knowledge of how metals influence star formation. Think of it this way: if metals are the paintbrushes of the universe, allowing stars to be drawn in a variety of shapes and sizes, then Caffau's star is like a painting that was somehow created before paint existed. It challenges the notion that metals are strictly necessary for small stars to form. And that's why it matters so much to astronomers, because it undermines one of the most basic assumptions about the relationship between metals and stars. In short, later generations of stars contain metals because they are the children of earlier stars. Each stellar death enriches the cosmos, adding a little more complexity to the next generation. Metals are the cosmic inheritance passed down through the ages, shaping not only the stars themselves but also the possibility of planets, chemistry, and life. The universe, in that sense, is a story of increasing richness, with each generation of stars writing a new chapter. And yet, in the middle of this story, Caffau's star appears like an ancient fossil, whispering that maybe some chapters were written differently than we thought. To truly appreciate why Caffau's star is such a cosmic riddle, we need to sit with the predictions that astrophysicists had long accepted as ironclad. The framework of the Big Bang theory, combined with decades of computer simulations and observational evidence, painted a very clear picture. In the early universe, small, long-lived stars should not exist if they were formed without metals. None. Zero. This wasn't some vague suggestion or loose hypothesis. It was a central tenet of how we thought the cosmos unfolded. Let's unpack why this was believed so strongly. The reasoning begins with the physics of star formation. When a gas cloud in space begins to collapse under its own gravity, it heats up. For that collapse to continue, the cloud must radiate away the excess heat, otherwise the rising pressure will counteract gravity and halt the process. In today's universe, metals such as carbon, oxygen, and iron play a crucial role here. Their atoms and ions can absorb and emit radiation efficiently, allowing energy to escape and the gas to cool. This cooling enables the cloud to fragment into smaller clumps, which then condense into individual stars of varying masses, including small ones like our Sun. But in the metal-free universe immediately after the Big Bang, that cooling mechanism wasn't available. The only elements around were hydrogen and helium, and they are notoriously poor at radiating away heat. Hydrogen molecules can help to some extent by radiating infrared light, but they aren't nearly as efficient as metals. The models showed that under these conditions, gas clouds wouldn't fragment into many small pieces. Instead, they would form only a few massive clumps, giving rise to very large stars. This led to the prediction that the first stars, the so-called population 3 stars, would be extremely massive, with tens to hundreds of times the mass of our Sun. Because massive stars burn through their nuclear fuel rapidly, they would live only a few million years before exploding as supernovae or collapsing into black holes. That meant none of them could possibly survive to the present day, 13 billion years later. Their role was to enrich the cosmos with metals, paving the way for smaller stars in subsequent generations. So here's the crucial point. Theory said that small, metal-free stars should never have formed. Without metals to cool the gas, there was no way to make a low-mass star that could burn quietly for billions of years. The only stars that could form were massive and short-lived. This wasn't just a speculative idea. It was backed by sophisticated numerical simulations of the early universe. Researchers would run models of primordial gas clouds collapsing under gravity, and every time the result was the same: massive stars, no small ones. This prediction became so deeply ingrained in astronomy that it was treated as settled knowledge. Observers never expected to find a low-mass, metal-free star, because the physics simply didn't allow for one. When astronomers searched for ancient stars, they looked for population 2 stars instead, stars that formed from gas enriched by the first supernovae, with very low but non-zero metallicity. Indeed, thousands of these extremely metal-poor stars have been found in the Milky Way's halo and in nearby dwarf galaxies. They provided a wealth of information about the nucleosynthesis of the first stars, indirectly confirming that population 3 stars were massive and short-lived. The absence of small, metal-free stars was itself considered evidence that the theory was correct. After all, if such stars could form, we should see them today. Low-mass stars can live for tens of billions of years, far longer than the current age of the universe. That means if even a handful of small population 3 stars had formed, they would still be out there, faintly glowing in the Milky Way. The fact that none were found seemed to confirm the prediction. They never formed in the first place. This logic was airtight, or so it seemed. Theory matched observation, and everything fit neatly into place. But then came the discovery of Caffau's star, and suddenly that neat picture began to unravel. Here was a star that was both extremely metal-poor and small, quietly burning away billions of years after its birth. According to all our models, it should not exist. It's as if nature had broken one of its own rules. For astrophysicists, this was not a minor anomaly. It was a direct contradiction of one of the most fundamental predictions of cosmic evolution. To put this into perspective, imagine building a bridge based on precise engineering calculations, and for decades, every bridge built according to those rules stands strong. Then, one day, you find a bridge standing in the middle of a valley, built without any of the required supports, and yet it hasn't collapsed in centuries. You'd be forced to ask, did we misunderstand the rules of engineering? Or is there some hidden factor at work that we hadn't accounted for? That's the dilemma Caffau's star presents. If the prediction was correct, this star cannot exist. And yet, it does. Which means either our models of early star formation are incomplete, or there are physical processes at play that we haven't fully understood. Perhaps metals aren't as absolutely necessary for cooling as we thought. Perhaps molecular hydrogen or dust grains played a larger role in the early universe than simulations suggested. Or perhaps there is some entirely new physics waiting to be uncovered. But the key takeaway here is this: according to established theory, no small, long-lived stars without metals should exist. This was a cornerstone of our understanding of the early universe. And Caffau's star stands in direct defiance of it. That's why this one faint star in the constellation of Leo has made such a big impact in astronomy. It's not just an oddball, it's a challenge to one of the most fundamental predictions about the birth of stars in our universe. The story of Caffau's star begins not with the star itself, but with the determined eyes of astronomers who were searching for relics of the ancient universe. For decades, scientists had been combing the skies for what are known as extremely metal-poor stars. Stars so deficient in heavy elements that they could serve as time capsules from the early epochs of cosmic history. The goal was not necessarily to find a surviving population 3 star, because, as we've already explored, the prevailing theory insisted that such stars should not exist, but rather to study stars from the second generation, the population 2 stars. These would bear the chemical fingerprints of the universe's first supernovae, revealing clues about what those massive population 3 giants had been like before they exploded. In 2011, a team of astronomers led by Italian researcher Elisabetta Caffau made a discovery that would shake the foundations of these expectations. They were using data from the Sloan Digital Sky Survey, SDSS, one of the most ambitious mapping projects of the sky ever undertaken. The SDSS had catalogued millions of stars, galaxies, and quasars, providing a treasure trove of information for astronomers worldwide. From this enormous dataset, researchers could identify candidate stars that appeared faint, old, and metal-poor, prime targets for more detailed spectroscopic follow-up. Caffau and her team focused their attention on a faint star in the constellation of Leo. Its spectrum, the light it emitted broken down into its component wavelengths, showed signs that it was extremely poor in metals. But when they looked closer, the result was even more shocking than they had anticipated. This star wasn't just metal poor. It was astonishingly metal poor, to the point where its chemical composition seemed to defy the predictions of established astrophysics. The official designation of the star, taken from the Sloan survey, is SDSS J102915+172927. It's a mouthful, and not exactly the kind of name that inspires wonder or curiosity in the general public. That's why it quickly became more commonly known as Caffau's star, in honor of the astronomer who led the team that brought it to light. In doing so, Caffau etched her name into the history of astronomy, because this star would go on to become one of the most perplexing and important stellar discoveries of the modern era. What made the star so extraordinary was not simply that it had low metallicity, but just how low it was. Caffau's star showed metallicity levels lower than any other star previously observed. In fact, it was found to contain less than 1/200,000th the amount of metals found in our Sun. To put that in perspective, imagine comparing 2 oceans. One is filled with salt, the other is nearly pure water with only a few grains of salt dissolved in it. That's the difference in metallicity between our Sun and Caffau's star. This was already remarkable enough. But then came the most shocking result of all. The star appeared to lack detectable amounts of elements that should have been present according to both theory and observation. Lithium, in particular, was almost completely absent, even though Big Bang nucleosynthesis predicts a universal abundance of lithium that should be found in all ancient stars. This absence raised eyebrows across the astronomical community, because it not only challenged star formation models, but also intersected with the long-standing cosmological lithium problem, the mismatch between predicted and observed lithium levels in the oldest stars. The discovery was announced in 2011 in a paper published in Nature, one of the most prestigious scientific journals. The impact was immediate. Here was a star that seemed to violate the established rules of stellar evolution. It was small and long-lived, when theory said that the first stars without metals should only have been massive and short-lived. It had virtually no metals at all, when population 2 stars were supposed to show at least some enrichment. And it lacked lithium, one of the very few elements expected to survive intact from the Big Bang itself. Astronomers were stunned. Some greeted the discovery with excitement, others with skepticism, but no one could deny its importance. The discovery of Caffau's star opened a door to questions that had long been considered closed. Was it possible that our models of the early universe were incomplete? Could small, metal-free stars actually form under certain conditions? Was this star a true relic of the first generation, or something even stranger that we hadn't yet considered? It's worth pausing here to recognize just how remarkable this moment was. Astronomy is a science that often confirms expectations. Observations of distant galaxies, the cosmic microwave background, or stellar populations usually fall into line with theoretical predictions. That's why the discovery of something that doesn't fit is so electrifying. It means there's more to the story than we realized. And in this case, that story begins with a faint star in Leo, identified in a massive survey, and brought to global attention by Elisabetta Caffau and her team. From that moment onward, the star would carry her name, not just as a label but as a reminder of the day when one astronomer's careful observation forced the entire scientific community to rethink what they thought they knew about the early universe. Every star in the sky that astronomers discover or study closely has a name, but not all names are created equal. Some stars have poetic titles rooted in ancient cultures, names like Betelgeuse, Sirius, or Vega. Others carry designations that seem more like strings of random numbers and letters than names, the product of vast astronomical surveys that catalogue billions of celestial objects. Caffau's star falls into the latter category. Its official designation is SDSS J102915+172927, and while that looks like an intimidating jumble of characters, there's actually a great deal of meaning packed into it. The SDSS part refers to the Sloan Digital Sky Survey, the ambitious project that first catalogued this star. Launched at the turn of the 21st century, the SDSS was designed to create the most detailed three-dimensional map of the universe ever attempted. Using a dedicated 2.5-meter telescope at Apache Point Observatory in New Mexico, it systematically scanned the sky, measuring the brightness, position, and spectrum of millions of stars and galaxies. Its impact on astronomy has been nothing short of revolutionary. Before SDSS, astronomers had catalogues of stars and galaxies, but never at this scale or depth. After SDSS, researchers had a cosmic treasure chest filled with the faint fingerprints of celestial objects stretching across much of the sky. Now, let's break down the rest of the designation. J102915+172927. At first glance, it may look like gibberish, but it's actually a precise celestial address. The J stands for the J2000 epoch, a standard astronomical reference frame based on the position of the celestial sphere as it appeared on January 1, 2000. Astronomers use this epoch as a fixed reference point so that catalogues remain consistent over time, since the positions of stars can drift slightly due to proper motion. The numbers that follow are essentially coordinates in the sky, tied to the system of right ascension and declination, the celestial equivalents of longitude and latitude on Earth. In this case, 102915 refers to the right ascension, which is like longitude but measured in hours, minutes, and seconds along the celestial equator. Plus 172927 refers to the declination, which is like latitude, measured in degrees north or south of the celestial equator. Put together, these numbers give astronomers a precise location for the star. Point your telescope to those coordinates, and you'll find SDSS J102915+172927. This system might seem dry, but it's essential for modern astronomy. When dealing with millions of stars, especially faint ones that don't stand out visually, you need a method that leaves no ambiguity. Imagine trying to find a single house in a vast city without street addresses. Nearly impossible. Catalogue designations like this provide the addresses of stars in the cosmic cityscape. What makes Caffau's star's catalogue name particularly important is not just its function as an address, but what it symbolizes about how the star was discovered. Unlike the bright stars visible to the naked eye that humans named thousands of years ago, Caffau's star was hidden, faint, and revealed only thanks to modern technology. Its catalogue name tells us that it wasn't stumbled upon by chance or ancient skywatchers, but by the systematic, computerized sweep of the Sloan survey. This is a star that embodies the age of big data in astronomy, where patterns and anomalies are found in massive datasets rather than through direct stargazing alone. The sterile string of characters, SDSS J102915+172927, also reflects a deeper truth. Caffau's star is not special because of its brightness or its place in mythology. It's special because of what its chemistry reveals about the early universe. Its significance lies in its spectrum, in the fact that its light contains almost no trace of the metals that should have been seeded by generations of stellar evolution. The catalogue name anchors it in the dataset, but its real identity is tied to the cosmic puzzle it represents. Of course, while professional astronomers rely on the designation, the nickname Caffau's star has stuck in popular discussions. Humans crave stories and connections, and a nickname is easier to remember than a coordinate string. More importantly, attaching Elisabetta Caffau's name to the star highlights the human element of discovery. It reminds us that behind every sterile designation in an astronomical catalogue lies the story of people asking questions, building tools, analyzing data, and ultimately being surprised by what the universe reveals. Still, the catalogue name serves an important symbolic role in this narrative. It reminds us that this discovery wasn't a matter of chance, it was the result of systematic exploration, of astronomers sifting through the digital universe catalogued by SDSS, looking for patterns that didn't quite fit. In a way, the name is a badge of the scientific process: precise, unromantic, and designed for utility. But it is also the starting point for a story that transcends its dry label, pulling us into one of the deepest mysteries of modern astrophysics. So while SDSS J102915+172927 might not roll off the tongue, it is the name etched into the official records of astronomy, the label by which this star will always be known in the scientific literature. It ties the star to the Sloan Digital Sky Survey, a project that transformed our view of the cosmos, and it encodes the exact coordinates where, against all odds, a star that shouldn't exist continues to shine. When we talk about stars, we often want to know not only what they are, but also where they are. It's one thing to describe a star's metallicity, its age, or its role in cosmic history, but for most of us, whether amateur stargazers or professional astronomers, there's a natural urge to look up and ask, where in the sky is this object? Can I see it? Caffau's star, for all its strangeness and mystery, does have a home in the night sky. Its official celestial address places it in the constellation of Leo, about 4,000 light-years away from Earth. That may not sound terribly far in cosmic terms. After all, our galaxy stretches over 100,000 light-years across, but it is far enough that this faint little star is invisible to the naked eye, requiring powerful telescopes and sensitive instruments to detect and study. To understand this location more clearly, let's first talk about the constellation of Leo. Leo is one of the oldest recognized constellations, and it has played a role in human culture for thousands of years. Its name means the lion, and it is easily recognizable in the night sky because its brightest stars trace out a pattern that resembles a crouching lion. The distinctive sickle-shaped curve of stars, marked by the bright Regulus at its base, represents the lion's manet, while a long triangle of stars to the east represents the body and tail. Leo is a zodiac constellation, meaning the sun passes through it on its annual journey across the ecliptic. That has made Leo important to ancient astrologers and skywatchers, but also a familiar fixture in the seasonal sky for people across cultures. Leo lies along the celestial equator, making it visible from most of the inhabited world. In the northern hemisphere, it is best seen in spring, while in the southern hemisphere, it is visible in the autumn months. When you look up at Leo, you are seeing a constellation filled with bright, relatively nearby stars, but hidden in the background, beyond the reach of the human eye, lies Caffau's star, a faint stellar relic tucked away in this region of the sky. Now, when astronomers say that Caffau's star lies in Leo, what they mean is that from our vantage point on Earth, its coordinates fall within the boundaries of that constellation. The star itself is not physically connected to the brighter stars of Leo in any real sense. Constellations are two-dimensional projections of three-dimensional reality, groupings that exist only in our perspective. The stars of Leo, like Regulus, Algebra, and Denebola, are at very different distances from us compared to Caffau's star. Regulus, for example, lies only about 79 light-years away, a cosmic neighbor compared to the much more distant Caffau's star. But because they happen to align along our line of sight, we place them in the same celestial neighborhood. At a distance of about 4,000 light-years, Caffau's star resides within the Milky Way galaxy, specifically in the galactic halo. The halo is the extended, roughly spherical region that surrounds the thin disk of our galaxy. Unlike the crowded star fields of the galactic plane, where the Sun is located, the halo is sparsely populated. It contains some of the oldest known stars, as well as globular clusters and vast amounts of dark matter. It is in this relatively quiet, ancient galactic neighborhood that Caffau's star drifts, far from the busy spiral arms and stellar nurseries where most young stars are born. The location in Leo also has practical importance for astronomers. Because Leo is a well-mapped and relatively accessible part of the sky, telescopes in both the northern and southern hemispheres can study this region. That means Caffau's star can be observed by a wide range of ground-based facilities, from Europe to the Americas to Asia. Its discovery in the Sloan Digital Sky Survey was only the first step. Follow-up observations with more powerful instruments, such as the Very Large Telescope, VLT, in Chile, were crucial to analyzing its spectrum and revealing its unusual chemical composition. Another way to appreciate its location is to think about what it means to say that the star is 4,000 light-years away. The light we see from Caffau's star today left it long before human civilization even existed. Around the time that light began its journey toward us, Earth was in the midst of its early Holocene epoch, just after the last ice age. Humans were transitioning from hunting and gathering to agriculture. By the time that light finally reached us in modern observatories, we had developed not only farming and cities, but also the technology to build telescopes and parse starlight into spectral fingerprints. That long journey of photons across space and time underscores the vast gulf between us and this ancient star. Despite this distance, 4,000 light-years is still close enough that we can study the star in detail with today's instruments. If Caffau's star were 10 times farther away, it might have been too faint to ever attract attention, its unique properties hidden from us forever. Its location in Leo, combined with its relative proximity within our galaxy, is therefore a stroke of luck. It allows us to peer into one of the oldest chapters of cosmic history using a star that still flickers faintly within reach of our telescopes. What's striking about Caffau's star's position is the contrast between its environment and its nature. On the one hand, it is located in the halo, a region populated by ancient stars, consistent with the idea that it is one of the oldest survivors in the galaxy. On the other hand, its extraordinary lack of metals makes it stand out even among halo stars, which are already known for being older and metal-poor compared to disk stars like the Sun. In other words, its home fits its age, but not its chemistry. This paradoxical combination makes its location in Leo a clue, but not an answer, to the puzzle it presents. When we connect all of this together, Caffau's star's position becomes more than just a set of coordinates. It reminds us that the night sky we see is layered with history. Bright modern stars in the foreground, faint ancient relics in the background, and the vast structure of the galaxy tying it all together. Somewhere in that tapestry, near the lion's manner of Leo, a star flickers quietly, one that by all rights should not exist, yet stubbornly does. When astronomers talk about why Caffau's star is special, they don't focus on its brightness, its color, or even its place in the sky. In fact, if you were to look at it through a telescope without special instruments, it wouldn't strike you as extraordinary at all. It's faint, small, and blends into the background of countless other stars. What makes Caffau's star remarkable, and why it has shaken the foundations of astrophysics, is its chemical composition. It is one of the most metal-poor stars ever discovered, a star with so little of the heavier elements that astronomers were stunned it could exist at all. In astronomy, the word metal-poor has a very particular meaning. It doesn't mean the star lacks iron jewelry or isn't shiny. It refers to its metallicity, the proportion of elements heavier than hydrogen and helium that it contains. The Sun, for example, is relatively metal-rich because it formed in a galaxy that had already gone through billions of years of star formation and death. Supernovae and stellar winds from previous generations of stars had enriched the interstellar medium with carbon, oxygen, iron, and countless other elements. Those metals were incorporated into the gas cloud that collapsed to form the Sun, planets, and ultimately us. That's why Earth is filled with iron cores, rocky crusts, oceans of water, and living beings made of carbon. All those elements came from earlier stars. Now imagine a star that seems almost completely devoid of those building blocks. That's what astronomers found when they studied Caffau's star in detail. Its spectrum revealed astonishingly low levels of metals, so low that it has been described as one of the least chemically enriched stars ever observed. Compared to the Sun, it contains 100,000 times less iron. To put that in perspective, if the Sun's iron content were represented by a solid mountain of metal, Caffau's star's iron could barely fill a small cup. This scarcity is not just unusual, it's extreme, and it places the star in a very rare category of objects. Why does that matter? Because metallicity tells us a story about a star's ancestry and age. A metal-poor star is like a fossil. It indicates that it formed at a time when the universe had not yet been enriched by multiple generations of supernovae. In other words, it must be very old. The extremely low metal content of Caffau's star suggests that it is either a direct survivor from the earliest epoch of star formation, or it formed from material that had been barely touched by the heavy elements of exploding massive stars. Either way, it carries a signature from a time when the cosmos was still young. But here's where the puzzle begins. According to theory, such a star shouldn't exist. As I mentioned in earlier segments, models of star formation suggested that stars with such low metallicity couldn't cool efficiently enough to collapse into small, long-lived stars like Caffau's. Instead, they were expected to form only massive, short-lived stars that would have died billions of years ago. In that sense, the mere presence of a tiny, dim, low-metal star with almost no metals is like finding a living dinosaur walking through your backyard. It contradicts the rules we thought governed stellar formation. Caffau star is not unique in being metal poor. Astronomers have found other stars with similarly low metallicities. However, it is special because of how extreme its deficiency is. Many other metal-poor stars, while poor in iron, still show noticeable traces of carbon, nitrogen, or oxygen. These elements can help the gas cloud cool and fragment, making star formation possible. Caffau star, on the other hand, seems to lack even these elements to a shocking degree. Its carbon and oxygen levels are so low that standard models say the gas cloud from which it formed shouldn't have been able to collapse into a small star at all. This makes it stand out even among its rare peers. The star's lack of metals also has a ripple effect in how we think about the early universe. Metals are crucial not just for star formation, but also for planetary formation and for the chemistry of life. A star like Caffau star would not have hosted rocky planets like Earth, nor would it have had the raw materials to seed complex chemistry around it. In that sense, its existence is a window into a very alien version of the universe, one where the familiar building blocks we take for granted were absent. To study this star is to look into a world before iron-rich planets, before carbon-based life, before the complex structures we now associate with galaxies and solar systems. Another reason Caffau star is so special is that it forces astronomers to question the boundaries of stellar classification. Traditionally, stars are grouped into populations. Population 1, metal-rich, like the Sun. Population 2, metal-poor, older stars in the halo. And population 3, the first stars, made only of hydrogen and helium, thought to have died long ago. Caffau star doesn't fit neatly into this scheme. It's technically population 2, but its chemical signature is so primitive that it looks more like something between population 2 and population 3. It is, in many ways, a missing link, a survivor that bridges the gap between the universe's first stars and the later generations. Astronomers sometimes call such stars stellar fossils. Just as paleontologists study dinosaur bones to learn about Earth's ancient past, astrophysicists study stars like Caffau's to learn about the early universe. But unlike fossils buried in rock, this fossil is still burning, still shining faintly in Leo's sky after more than 13 billion years. Its light carries information encoded in its spectrum, and every atom inside it tells a story about conditions in the young cosmos. To grasp just how rare such stars are, consider this. Our galaxy has between 100 billion and 400 billion stars, yet only a handful have been identified with such extreme metal deficiencies. The rarity makes each one precious. Caffau's star is not just another dot in the sky, it's a Rosetta Stone, offering clues about processes we thought we understood but apparently don't. And so, what makes Caffau's star special is not its brightness, not its size, and not its distance. It is special because it defies our expectations. It is special because it challenges our theories about the Big Bang, star formation, and cosmic evolution. It is special because it is one of the purest windows into the early universe that we have ever found, a fragile ember from a time when the cosmos was still taking its first breaths. When astronomers talk about stars, one of the most important terms they use is metallicity. It's a word that can sound confusing at first, because in everyday life, we think of metals as things like iron, copper, or gold. In astronomy, though, the definition is far broader and far simpler. Any element heavier than hydrogen and helium is called a metal. That means oxygen, carbon, nitrogen, silicon, iron, all of them count as metals in the astrophysical sense. So when astronomers say a star has low metallicity, they mean it contains very few of those heavier elements and is instead made almost entirely of hydrogen and helium. This definition comes directly from the history of the universe. After the Big Bang, the cosmos contained almost nothing but hydrogen and helium, with tiny traces of lithium. All the other elements, everything from the carbon in your body to the oxygen in the air to the iron in your blood, were forged later, inside stars or in the explosions of dying stars. In that sense, metallicity is more than just a measure of chemical composition. It is a timeline marker. It tells us whether a star was born in a young universe, when heavy elements were rare, or in a later universe, when stellar generations had already enriched the interstellar medium with metals. To quantify metallicity, astronomers use a notation that compares a star's abundance of iron relative to hydrogen with that of the Sun. This is written as Fe or H, where Fe stands for iron and H for hydrogen. The reason iron is used as the benchmark is that iron produces many easily detectable spectral lines, making it practical to measure in starlight. A star with FeH equals 0 has the same iron to hydrogen ratio as the Sun. A star with FeH equals -1 has only 1/10 the Sun's iron. A star with FeH equals -2 has 1/100th, and so on. Each decrease of 1 in this logarithmic scale represents a factor of 10 less iron compared to hydrogen. Caffau's star has a metallicity so low that its FeH value is around -5. This means it contains only about 100,000th the iron of the Sun. That is an astonishingly small amount, and it places the star in a category of what are called ultra-metal-poor stars. Very few stars with metallicities this low have ever been discovered, making Caffau's star an extreme outlier. Why does metallicity matter so much to astronomers? The answer is that metallicity acts as a kind of cosmic fingerprint. It reveals not just the age of a star, but also the conditions of the environment in which it formed. High metallicity stars, like the Sun, are younger in cosmic terms and formed in a galaxy that had already been enriched by billions of years of stellar recycling. Low metallicity stars, on the other hand, are older, formed when the galaxy and the universe were still chemically primitive. By measuring metallicity, astronomers can piece together the history of star formation, galaxy evolution, and the buildup of the elements over billions of years. Metals also matter for stellar physics. They influence how stars form, how they shine, and how they die. For example, metals provide a way for gas clouds to cool. When a cloud of hydrogen and helium begins to collapse under gravity, it heats up. If the cloud can't radiate away that heat, it resists further collapse. Metals like carbon and oxygen allow the gas to radiate energy more efficiently, cooling it and enabling it to fragment into smaller clumps that can form stars. This is why theory predicts that without metals, only very massive stars could form in the early universe. Metals also play a role inside stars themselves. They affect the opacity of stellar material, that is, how easily radiation passes through it. In metal-rich stars, radiation interacts more strongly with atoms, changing the balance of energy transport and slightly altering the star's structure and lifetime. Metals contribute to nuclear reactions as well, particularly in advanced stages of stellar evolution. In massive stars, fusion pathways like the carbon-nitrogen-oxygen (CNO) cycle depend on the presence of those heavier elements. Without them, stars burn differently, evolve differently, and die differently. For planets and life, metallicity is even more crucial. A star with very low metallicity almost certainly could not host an Earth-like planet. Rocky planets require elements like silicon, magnesium, and iron to build their crusts and cores, while water requires oxygen, and life as we know it depends on carbon, nitrogen, and phosphorus. That's why astronomers searching for potentially habitable exoplanets focus on stars with at least some enrichment of metals. The fact that Caffau's star is so metal-poor means it could never have hosted a planetary system like ours. It is, in essence, a relic from a time before planets and life were possible. In practical terms, astronomers measure metallicity by studying a star's spectrum. When starlight is split into its component colors, it reveals a series of dark absorption lines, each corresponding to a particular element absorbing light at specific wavelengths. By analyzing the strength of these lines, scientists can determine the abundances of various elements. For a star like the Sun, the spectrum is filled with lines from iron, calcium, sodium, magnesium, and more. For Caffau's star, the spectrum is astonishingly bare. The absence of lines is itself a revelation. It tells us that the star is missing the ingredients most other stars possess in abundance. This is why Caffau's star became such a shock. Its metallicity was not just low, it was so low that existing theories said such a star shouldn't exist. With essentially no metals to cool the gas cloud, how could such a small, long-lived star ever have formed? This is the heart of the mystery, and it is what makes metallicity the central concept in understanding Caffau's star's significance. So, metallicity in astronomy is more than a chemical label. It is a measure of cosmic time, a guide to stellar evolution, a key to planetary formation, and a test of our theories about the early universe. In the case of Caffau's star, its metallicity isn't just a number. It is the clue that reveals why this faint star has become such a profound challenge to our understanding of the cosmos. When astronomers first measured the spectrum of Caffau's star, they expected to see at least faint hints of certain elements. Even in the most ancient and metal-poor stars known, there is usually some detectable presence of carbon, oxygen, or lithium. These elements are not just nice-to-have features in the chemistry of the cosmos, they are expected outcomes of how the universe and stars evolve. But when Elisabetta Caffau and her team analyzed the data from the Very Large Telescope in Chile, what they saw was so stark, so barren, that it left them stunned. Caffau's star showed almost no detectable lithium, carbon, or oxygen. It wasn't just low in these elements, it was practically empty of them. This was shocking because these particular elements carry deep significance in both cosmology and stellar physics. Each one tells a different part of the universe's origin story, and the near absence of all three in a star that should have them challenges some of the most carefully constructed narratives of modern astrophysics. Let's start with lithium. According to the theory of Big Bang nucleosynthesis, the first 3 minutes after the Big Bang produced hydrogen, helium, and a small but definite trace of lithium. This lithium should be found in roughly the same proportions in all the oldest stars because it predates them. It was there before the first stars even formed. Astronomers expected Caffau's star, being ancient and metal-poor, to hold onto this primordial lithium like a time capsule. But instead, they found the opposite. Its lithium abundance was so low that it was effectively absent. That's not just strange, it's contradictory. It's like digging into the oldest layers of Earth's crust expecting to find fossils of primitive organisms, only to find nothing at all. Lithium has long been a headache for cosmologists. There's a well-known problem called the cosmological lithium problem, where the measured lithium abundance in old stars doesn't quite match what theory predicts from the Big Bang. But Caffau's star takes this problem to an extreme. The lithium levels aren't just mismatched, they're missing almost entirely. It's as if the star swallowed, destroyed, or somehow never received the lithium it was supposed to have, and no current model explains this fully. Now let's look at carbon and oxygen. These two elements are crucial in another way, they help gas clouds cool. When a massive cloud of gas begins collapsing under gravity, the heat builds up, and without some mechanism to release that heat, the collapse stalls. Carbon and oxygen, through their atomic transitions, can radiate energy away, allowing the cloud to cool enough to fragment and form smaller stars. That's why, in most ultra-metal-poor stars found so far, astronomers usually see some enrichment in carbon or oxygen. Even if they're low in iron, they have at least a bit of carbon or oxygen, enough to explain how the star's parent cloud cooled and collapsed. Caffau's star, however, doesn't follow this rule. Its carbon and oxygen abundances are not just low, they are undetectable in the spectrum. The gas cloud that gave birth to it had virtually none of these cooling agents, and yet the star formed anyway. That defies the very models astronomers have used to explain how the first small stars could exist. According to those models, a star like Caffau's star shouldn't have been possible. Without carbon or oxygen to help cooling, the cloud should have either failed to collapse or produced only massive, short-lived stars that would have exploded long ago. Yet here is Caffau's star, small, dim, and still alive after more than 13 billion years. The triple absence, lithium, carbon, oxygen, is what makes the star's spectrum so shocking. Each missing element raises a different contradiction. No lithium, a direct challenge to Big Bang nucleosynthesis. No carbon or oxygen, a direct challenge to models of star formation. Put together, they suggest that either we are missing a key piece of physics or that our current models need major revision. Consider also how unique this combination is. Other known extremely metal-poor stars, like E1327-2326 or He0107-5240, still show enhanced carbon levels. These stars were used to build the idea that even the earliest small stars could form if carbon and oxygen provided the cooling. Caffau's star stands apart because it refuses to fit even this adjusted model. It's not just an oddball, it's an outright outlier that refuses to sit neatly in any category we've built. The absence of these elements also raises questions about stellar evolution itself. Could it be that Caffau's star originally had more lithium, carbon, or oxygen but somehow lost them? Did internal processes deplete the lithium? Did the star's outer layers mix differently than expected? Or was the gas cloud it formed from genuinely so pristine that it contained almost nothing beyond hydrogen and helium? Each possibility has implications that ripple through cosmology, nucleosynthesis, and galactic archaeology. The sheer shock of Caffau's star's composition is why its discovery in 2011 was not just another incremental step in astronomy but a disruptive revelation. The data forced scientists to confront the uncomfortable truth that nature had produced something their equations said shouldn't exist. This is not a small detail, not a minor footnote in the ledger of cosmic knowledge. It's a glaring contradiction that continues to spark debate more than a decade later. And so, the shocking result is this: Caffau's star isn't just metal poor. It's element poor in the most fundamental way, lacking even the elements that should have been guaranteed by the Big Bang or necessary for star formation. That is why it continues to haunt astronomers' imaginations. In its faint, quiet light, it carries the message that our understanding of the universe's earliest moments may be incomplete, or perhaps even deeply flawed. Lithium is one of those deceptively simple elements that hides an enormous amount of cosmological significance. On the periodic table, it's just element number 3, light, fragile, and not something you'd think of as central to the story of the cosmos. Yet in cosmology, lithium plays a starring role, because it stands at the crossroads between the Big Bang itself and the later evolution of stars. It acts like a signature, a chemical receipt, if you will, for the conditions in the infant universe. And this is why Caffau's star's near-total lack of lithium is so unsettling. It's like finding a historical record where the ink is missing from the most important line. To see why lithium matters, we have to return to the very beginning, to the first few minutes after the Big Bang. During that brief window, the universe was unimaginably hot and dense, filled with a plasma of protons, neutrons, electrons, and radiation. In those conditions, nuclear reactions happened everywhere, fusing protons and neutrons into light nuclei. This process is what scientists call Big Bang nucleosynthesis, BBN. It's one of the 3 great pillars of evidence for the Big Bang model, along with the cosmic microwave background and the expansion of the universe. BBN predicted, and observations confirm, that the early universe produced roughly about 75% hydrogen, by mass, about 25% helium-4, trace amounts of deuterium, hydrogen with a neutron, and helium-3, and, crucially, a very small but measurable fraction of lithium-7. This prediction is one of the most precise triumphs of theoretical physics. The abundances of hydrogen, helium, and deuterium match the calculations almost perfectly when compared to what astronomers observe in the oldest stars and interstellar gas. Lithium, however, has always been the odd one out. Observations of old stars consistently find less lithium than theory predicts, about 3 times less. This discrepancy is known as the cosmological lithium problem. Now here's where Caffau's star deepens the mystery. The so-called Spite Plateau, named after astronomers Monique and Francois Spite, who studied old stars in the 1980s, describes the relatively constant lithium abundance found in metal-poor stars across the galaxy. These stars, thought to be very old, typically show the same lithium fraction, which is lower than the theoretical prediction but still detectable. It's like they all carry the same cosmic fingerprint, albeit one that doesn't quite match the model. Caffau's star should have sat on this plateau. Instead, it dropped off entirely. Its lithium content wasn't just lower than expected, it was practically absent. The star's spectrum revealed no sign of the fragile element. That's more than a small mismatch, it's a total break with the expected pattern. If the Spite Plateau represents a rule of the cosmos, Caffau's star is a blatant exception. Why does this matter so much? Because lithium is a rare bridge element between the physics of the very early universe and the chemistry of stars. Its presence or absence tells us something about both. If Caffau's star never had lithium, that would mean our understanding of Big Bang nucleosynthesis is missing a key piece, that perhaps under certain conditions, lithium simply wasn't produced, or it was destroyed before stars even formed. But BBN is supposed to be a universal process. The laws of physics don't change from one patch of the cosmos to another. So how could one star escape it? Alternatively, if Caffau's star did originally contain lithium but lost it later, that suggests something unusual happened inside the star itself. Lithium is a fragile element. Unlike helium or carbon, it can be easily destroyed at relatively low temperatures inside stars. If material from deeper layers of the star was mixed into the outer layers, it could erase the lithium signature. But here's the problem. Caffau's star is a small, quiet, uneventful star. It's not supposed to have undergone the kind of turbulent mixing or extreme processes that would destroy all its lithium. It has lived a long, stable life. So why is the lithium gone? This is why lithium is such a linchpin. It's not just about one element. It's about whether the narrative from the Big Bang to the present holds together. Caffau's star effectively says, "Your universe should have left me with lithium, but I don't have it." That calls into question either the cosmology, how the element was made in the first place, or the stellar astrophysics, how the element survived billions of years. Neither explanation is comfortable, and both suggest gaps in our understanding. Let's also put this into perspective with other stars. Astronomers have studied hundreds of extremely metal-poor stars. While many show the lithium discrepancy of the Spike Plateau, they don't erase lithium entirely. Even stars with metallicities almost as low as Caffau's star usually retain some lithium. That makes Caffau's star even more exceptional. It's not just part of the lithium problem, it's a new category of problem all on its own. This is why astronomers emphasize the star's lithium deficiency when talking about its significance. Iron and carbon and oxygen tell us about star formation and galactic evolution. But lithium reaches all the way back to the first 3 minutes of the universe. If Caffau's star lacks it, then we are faced with the possibility that something about those earliest minutes, or about our understanding of how stars preserve their primordial ingredients, is incomplete. And here's the final twist. Lithium isn't just a curiosity for cosmologists. It's also an element we use on Earth every day, in batteries, in medicine, and in industry. The lithium in your phone battery and the lithium in Caffau's star both trace their origins back to the dawn of time. That makes its absence in this star not just an academic puzzle, but a profound reminder that the universe's chemistry is more complex and mysterious than we imagined. Here is where the story of Caffau's star turns from puzzling to downright paradoxical. For decades, astrophysicists have been fairly confident in one prediction. Stars like this, tiny, long-lived, nearly devoid of metals, should not exist. And yet, there it is, quietly shining in the constellation Leo, as if mocking our theoretical frameworks. This contradiction between prediction and observation lies at the heart of why Caffau's star is so famous, and why it continues to haunt scientific discussions more than a decade after its discovery. To understand the contradiction, you have to look closely at the process of star formation as understood through theory. Stars are born when massive clouds of gas collapse under their own gravity. But gravity alone isn't enough to form a star. If the gas cloud just collapses inward without cooling, the pressure from heat will eventually counteract the pull of gravity, halting the collapse before the star can ever ignite nuclear fusion. Cooling is therefore the key that allows gravity to win, shrinking the gas into a dense enough core to trigger the fusion of hydrogen into helium. In the earliest universe, after the Big Bang, the only elements available for this process were hydrogen, helium, and a trace of lithium. But here's the problem. Hydrogen and helium are notoriously poor coolants. They don't have the atomic complexity to radiate away large amounts of energy as efficiently as heavier elements like carbon or oxygen. For this reason, theory has long held that the first stars, the so-called population 3 stars, had to be massive. Their huge gravity could overcome the inefficiency of cooling, collapsing the cloud into dense, short-lived giants. These stars would then burn through their fuel rapidly and explode as supernovae, enriching the cosmos with heavier elements. This led to a kind of law in stellar astrophysics. Small, long-lived, low-metal stars should not form directly out of pristine hydrogen and helium. They needed metals to help cool the gas clouds. In other words, the very existence of a star like Caffau's star, which is extremely low in metals, flies directly in the face of this understanding. It appears to belong to the small, long-lived category, a category that the model said couldn't happen without carbon, oxygen, or other coolants. This is why Caffau's star is such a contradiction. It doesn't just have less metal than expected. It seems to have formed under conditions where, by all accounts, no star like it should have been able to form at all. It is like finding an oak tree in the middle of the Sahara Desert, or an iceberg floating on a lake in the tropics. Its very existence demands either that our models of star formation are incomplete, or that some unknown process occurred in the early universe that allowed such stars to emerge against the odds. The contradiction becomes even sharper when you realize that Caffau's star is not just low in metals, but also missing the carbon and oxygen escape hatch that astronomers had used to reconcile theory with observation. Before its discovery, Extremely metal-poor stars were often explained as the result of special conditions. Maybe the parent gas clouds contained just enough carbon or oxygen, injected by the very first supernovae, to allow them to cool and form smaller stars. This carbon cooling model seemed to solve the puzzle. But Caffau's star refuses to play along. With no detectable carbon or oxygen, it closes that loophole. It forces us back to square one. Think about what this means. For Caffau's star to exist, the gas cloud that formed it must have found a way to collapse without the help of metals, carbon, or oxygen. According to theory, that gas should have remained too warm and diffused to form a small star. The collapse should have failed, or at best, produced a massive star that lived fast and died young. Yet the result was something completely different. A small, quiet star still burning more than 13 billion years later. The contradiction is not a minor detail in the margins of astrophysics textbooks. It threatens to undermine the foundations of how we think star formation began in the first place. If one such star exists, then our models missed something fundamental. And if more like it exist, if Caffau's star is not alone, then the entire theoretical framework of population 3 and early population 2 star formation may need a radical overhaul. To scientists, contradictions like this are both terrifying and thrilling. Terrifying because they expose weaknesses in carefully built models. Thrilling because they point the way toward new discoveries. But the contradiction of Caffau's star is especially potent because it links together so many fields. The physics of the Big Bang, the chemistry of the early universe, the evolution of galaxies, and the lifetimes of stars. It is not a small piece of the puzzle that can be patched up easily. It is a loose thread that, if pulled, could unravel the entire fabric of our cosmic origin story. And yet, the star exists. Its light has traveled 4,000 years to reach us, carrying with it a message from the early universe that we cannot ignore. The contradiction it represents is not abstract. It is etched into the very atoms of the star. Each missing element, each spectral line that should be there but isn't, is a reminder that the universe does not always conform to our neat equations. That is why astronomers speak about Caffau's star with such a mix of frustration and awe. They know what the theory says, and they see the evidence with their own eyes. The contradiction is real, and until it is resolved, it stands as a challenge. Either refine the theory, expand it, or admit that we have misunderstood something profound about how the cosmos gave birth to its first generations of stars. The formation puzzle at the heart of Caffau's star is one of the most stubborn mysteries in astrophysics. To put it plainly, low metallicity gas clouds shouldn't cool enough to collapse into small stars. And yet, Caffau's star is sitting right there in Leo, existing as living proof that something we thought was impossible somehow happened. To understand why this is such a problem, we need to walk through the physics of star birth in painstaking detail, and then explore why this little star throws the whole framework into disarray. When gas clouds collapse to form stars, the competition is always between two forces, gravity and pressure. Gravity wants to pull the gas inward, making it denser and hotter. Pressure, generated by the heating of the gas, pushes outward, resisting collapse. For gravity to win, and for the cloud to continue collapsing all the way to the point where nuclear fusion can ignite, the gas must be able to shed heat efficiently. If it can't radiate away the energy, the temperature and pressure rise too quickly, halting collapse before a star is born. This is where metallicity comes into play. Heavy elements like carbon, oxygen, silicon, and iron provide many ways for gas to cool. Their electrons can jump between energy levels and emit photons, allowing the gas to lose energy and temperature. Even tiny traces of metals in a gas cloud make the collapse easier, allowing gravity to pull the cloud into smaller, denser clumps. This is why the second and third generations of stars, population 2 and I, could form stars of all sizes, from massive giants to small red dwarfs like the ones we see today. Metals gave the universe a kind of cooling toolkit that opened up many pathways for star formation. But what about the first stars, which had no metals? That's where the puzzle begins. Without carbon or oxygen, gas clouds had only hydrogen and helium to work with. And those two elements are terrible coolants under normal star-forming conditions. Hydrogen molecules, H, can provide a bit of cooling, but only in very specific circumstances, and certainly not enough to allow the gas to fragment into small, long-lived stars. Instead, theory predicted that primordial gas clouds would collapse into massive clumps, forming stars tens or even hundreds of times the mass of the Sun. These giants would burn hot and fast, living only a few million years before exploding as supernovae and seeding the cosmos with metals. So according to the theory, the first generation of stars, population 3, should have been enormous and short-lived. Their deaths would then enrich the interstellar medium with metals, enabling the next generation of stars to form in more diverse sizes. But here's the contradiction. Caffau's star looks like it belongs to that very first era of star formation. It has almost no metals, no carbon, no oxygen, no lithium, essentially a chemical fingerprint from the early universe. Yet it is small and long-lived, the exact kind of star that shouldn't have been able to form without metals. This is the formation puzzle. If low metallicity gas clouds can't cool effectively, then how did this star form? Why didn't the gas that birthed Caffau's star simply collapse into a massive giant that died billions of years ago? Why did it instead produce a tiny star that has endured for more than 13 billion years? Astronomers have tried to imagine possible solutions. One idea is that molecular hydrogen might have been more effective at cooling in certain early environments than we currently think. If the gas cloud that formed Caffau's star was unusually rich in H molecules, perhaps it could radiate enough heat to allow collapse into a small star. But the problem with this idea is that molecular hydrogen is easily destroyed by ultraviolet radiation, which would have been abundant in the early universe thanks to the first massive stars. So while it's possible, it doesn't explain how a star like Caffau's could form and survive in such a harsh environment. Another idea is that dust grains played a role. Even in a metal-poor environment, tiny amounts of dust could have formed in the explosions of the very first supernovae. Dust is an excellent coolant, as it can radiate away heat very efficiently. If the gas cloud that formed Caffau's star contained even a minuscule fraction of dust, perhaps that was enough to tip the balance, allowing collapse into a small, dense clump. But this explanation also has issues, because Caffau's star shows no evidence of enrichment from earlier supernovae. Its chemical makeup is just too primitive. The most baffling aspect of the formation puzzle is that it seems to require two contradictory things to be true at once. On the one hand, Caffau's star looks chemically pristine, as if it formed directly from primordial gas with almost no input from earlier stars. On the other hand, its very existence suggests that some additional cooling mechanism, metals, dust, or something else, must have been at play. It is as if the star is saying, I was born in the early universe, before metals existed, but I also used a process that shouldn't have been available to me. That's why it is so infuriatingly difficult to explain. The formation puzzle of Caffau's star highlights the limits of our simulations of the early universe. Computer models of star formation can reproduce the general picture: massive population 3 stars, supernova enrichment, the rise of later generations, but they struggle to create stars like this. Even the best simulations rarely produce low-mass, metal-poor stars that could survive to the present day. And yet, we're looking at one through our telescopes. It raises an uncomfortable question. Could it be that our models of physics, chemistry, or cooling in the early universe are missing a piece? Could there be some unknown process, some subtle atomic or molecular interaction, that allowed certain gas clouds to collapse into small stars against the odds? If so, then Caffau's star is not just an anomaly, it's a clue. It's pointing us toward something new in the physics of star formation. This is why astronomers keep calling Caffau's star a puzzle. It is not just unusual, it is a direct challenge to our understanding of how the cosmos made its first stars. Until we solve the riddle of how low metallicity gas could cool enough to form such a small, ancient star, our picture of the universe's earliest chapters remains incomplete. Caffau's star does more than just raise eyebrows. It directly challenges the very models we use to understand early star formation. When astronomers build models of the cosmos, they rely on a combination of physics, chemistry, and computer simulations to reconstruct how gas clouds collapse, how stars ignite, and how galaxies assemble. These models aren't speculative fantasies, they're carefully grounded in equations of gravity, thermodynamics, atomic physics, and radiative transfer. They've been refined over decades, and they've been tested against many observations of stars and galaxies. Yet, here comes this quiet little star, and suddenly the models look incomplete, maybe even flawed. Let's begin with what the models say. According to the current framework, the early universe after the Big Bang produced only hydrogen, helium, and trace lithium. Without heavier elements, what astronomers collectively call metals, the gas clouds in that era should have lacked efficient cooling channels. As a result, simulations consistently show that these clouds collapse into massive stars, typically 30 to 300 times the mass of the Sun. These population 3 stars, in turn, would live short, brilliant lives, producing heavy elements through nuclear fusion, and then explode as supernovae. This narrative is crucial because it explains the observed transition from a universe of pure hydrogen and helium to one filled with stars, planets, and eventually life. It's a linchpin in the cosmic timeline. No massive population 3 stars, no enrichment, no planets, no us. But what this framework doesn't allow for is a star like Caffau's star, a small, faint, long-lived star with almost no metals, still shining 13 billion years later. The challenge is glaring. The models say, stars like this shouldn't exist. The telescope says, here it is. That tension between prediction and observation is the kind of scientific earthquake that forces researchers back to the drawing board. Think about what this implies. If Caffau's star truly formed from nearly pristine gas, as its chemical fingerprint suggests, then our models of star formation at low metallicity must be missing a key ingredient. Maybe our understanding of cooling mechanisms is incomplete. Maybe our simulations don't capture certain small-scale processes that happen in real interstellar gas clouds. Or maybe the physics we take for granted, the interactions between gas, gravity, and radiation, needs to be reconsidered in some subtle but important way. One of the most important aspects of this challenge is the way it undermines the neat categorization of stellar populations. Astronomers like to sort stars into population 3, the first, metal-free giants, population 2, the next generation, metal-poor but enriched, and population 1, like the Sun, metal-rich. But Caffau's star seems to exist in a grey area between those categories. It is chemically so primitive that it looks like a population 3 relic, yet structurally it resembles a population 2 dwarf. It refuses to fit neatly into the boxes that models provide. And whenever nature refuses to fit into our boxes, it's a sign that the boxes themselves are flawed. The challenge grows even deeper when you consider the rarity of such stars. If models are correct, then the fraction of stars like Caffau's should be essentially zero. They should simply never form. And yet, we've found one. This suggests 2 possibilities. Either Caffau's star is an absurdly rare fluke, the cosmic equivalent of winning the lottery a million times over, or the models are wrong, and such stars are more common than we think, we just haven't detected them yet. Astronomers lean toward the second option, because science tends to distrust explanations that rely on sheer luck. If Caffau's star exists, then there might be more like it, hidden in the faint recesses of the Milky Way halo. If more are found, then the models will need to be rewritten entirely, because they cannot explain how these stars formed and survived for billions of years. What makes the challenge so fascinating is that it's not just about tweaking a few parameters. You can't just adjust a number here or there in the equations and suddenly get Caffau's star to pop out of a simulation. It may require rethinking entire assumptions, about how gas cools, about how turbulence shapes clouds, about the role of dust or molecular hydrogen, or even about exotic physics like dark matter interactions. This is the kind of anomaly that could either expand existing models, or spark the birth of a whole new framework for cosmic origins. The star also challenges the predictive power of cosmology. The Big Bang theory itself is not necessarily undermined, but the models built on top of it, particularly those concerning the formation of the first stars, are exposed as incomplete. It's like discovering a fossil of an animal that shouldn't exist according to evolutionary theory. The theory of evolution itself might still stand, but the details of how species emerged would need a major revision. Likewise, Caffau's star forces astrophysicists to confront the fact that their story of the first light in the universe is not the full story. Another way this challenges models is through the role of lithium. According to Big Bang nucleosynthesis, there should be a predictable abundance of lithium in old stars. Caffau's star is lithium poor in ways that defy expectation. This means that not only is the cooling problem unsolved, but the very chemistry of the early universe might need revisiting. If we cannot account for lithium in a star like this, then our nuclear reaction networks in the early universe might also need to be re-examined. The scientific community takes anomalies like this very seriously, not because they want to throw away decades of work, but because anomalies are where progress happens. Every major leap in physics, from relativity to quantum mechanics, began with a stubborn contradiction that the old models couldn't explain. Caffau's star is precisely that kind of contradiction for cosmology and stellar astrophysics. And the challenge isn't going away. As telescopes become more powerful, and as surveys of the Milky Way's halo expand, it's possible we'll find more stars like Caffau's. If we do, the pressure on existing models will grow unbearable. At that point, astrophysicists won't just be fine-tuning their equations. They'll be forced to rethink how the universe's very first stars came into being. Caffau's star is more than an anomaly. It is a cosmic red flag, waving at our carefully built theories, demanding that we take a second look. And in doing so, it may one day lead us to a deeper, richer understanding of how the universe transitioned from darkness to light. When astronomers first encountered the strange existence of Caffau's star, their immediate reaction wasn't to throw out the Big Bang model or discard decades of astrophysics. Instead, the instinct was to ask, could there be alternative explanations? If this star formed under conditions that theory says are impossible, maybe the theory is missing some overlooked mechanism that allowed a cloud of nearly pristine gas to cool and collapse into a small, long-lived star. Two leading candidates have emerged in these discussions: molecular hydrogen and dust. Both play roles in star formation today, but their effectiveness in the primitive, metal-poor universe remains deeply debated. Let's start with molecular hydrogen, H. Hydrogen was, of course, the dominant element after the Big Bang. Most of it existed as single atoms, but under the right conditions, hydrogen atoms can pair up to form molecules. Molecular hydrogen has a special property: it can act as a coolant. When H molecules collide, they can radiate away energy in the form of infrared light. This allows a collapsing gas cloud to lose heat, lowering its internal pressure, and giving gravity the upper hand. In modern star formation, molecular hydrogen cooling is an essential step in the collapse of cold, dense gas clouds. So the idea goes like this: perhaps the cloud that formed Caffau's star contained an unusually high fraction of molecular hydrogen, enough to let it shed heat efficiently even without metals. This would have allowed the cloud to fragment into smaller pieces, one of which became the tiny star we now observe. But there's a snag. In the early universe, molecular hydrogen was incredibly fragile. The very first massive stars, the population 3 giants, produced copious ultraviolet radiation. This radiation easily tore H apart in a process called photodissociation. In other words, the earliest stellar light flooded the cosmos with UV photons that broke apart hydrogen molecules before they could accumulate in significant amounts. That makes it hard to explain how a gas cloud could preserve enough molecular hydrogen to cool effectively. Unless the region that gave birth to Caffau's star was somehow shielded from that radiation, the H explanation doesn't hold up well. That leads to the second possibility: dust. Dust in astronomy doesn't mean the stuff you wipe off your bookshelf. It refers to tiny grains of solid material, often made of carbon, silicon, or oxygen compounds. Even in trace amounts, dust grains are incredibly efficient radiators of heat. They absorb energy from their surroundings and re-emit it as infrared radiation, cooling the gas around them. Dust also helps molecules like H form on their surfaces, making it doubly useful in star formation. In the modern Milky Way, dust is everywhere, forged in the outer layers of stars and ejected into space by stellar winds and supernova explosions. But in the early universe, where would dust have come from? The answer lies in the first massive stars. When those giants exploded as supernovae, they would have seeded the cosmos with the first grains of dust. Even if the total amount was tiny, it could have been enough to alter the cooling dynamics of some gas clouds. So perhaps the cloud that birthed Caffau's star wasn't purely primordial. Maybe it had been kissed by the ashes of an earlier generation of stars, not enough to leave heavy elements in detectable amounts, but enough to sprinkle a faint dusting of grains that tipped the balance during collapse. The dust grains would have provided just enough cooling power to allow the cloud to fragment into smaller clumps, one of which condensed into a star small enough to survive until today. This explanation has a certain elegance, but it also carries its own contradictions. If dust came from supernovae, then we would expect to see traces of heavy elements in Caffau's star, but it has virtually none. Its chemical fingerprint is as primitive as it gets. How could dust exist without leaving behind any detectable metals? Did the dust form in some unusual way, perhaps dominated by elements that aren't showing up in our spectral measurements? Or did the star form in a pocket of space where dust had been deposited, but metals somehow remained diluted? These are the kinds of questions that keep theorists awake at night. There's also a third line of speculation, often less discussed but equally intriguing. Perhaps some unknown cooling process was at work. It's possible that our understanding of atomic and molecular physics under extreme conditions isn't complete. Could exotic molecules, overlooked radiation mechanisms, or interactions with dark matter have played a role? These ideas remain highly speculative, but the mere existence of Caffau's star invites speculation. After all, if the star itself is impossible, maybe the physics that produced it is something we haven't discovered yet. What's especially compelling about these alternative explanations is how they highlight the delicate balance that governs star formation. Cooling is everything. The universe is essentially one long struggle between gravity, trying to pull gas together, and heat, trying to push it apart. Metals, dust, molecules, these are the tools that let gravity win by letting gas shed its heat. Without them, collapse stalls, and stars never ignite. With them, collapse succeeds, and the universe lights up. Caffau's star is proof that somehow, against the odds, gravity found a way to win billions of years ago, without the cooling tools we thought were necessary. Each proposed explanation, molecular hydrogen, dust, or something entirely unknown, comes with its own challenges. Molecular hydrogen is too fragile, dust should have left more chemical fingerprints, and exotic processes are speculative at best. None of them fully solves the puzzle. And yet, the alternatives are critical to explore, because they represent the only pathways we have to bridge the gap between observation and theory. At its core, the search for explanations is not just about one star. It's about whether the models we use to understand the first billion years of cosmic history are trustworthy. If a single star like Caffau's requires new physics or overlooked processes, then perhaps entire populations of ancient stars formed under conditions we don't yet grasp. The implications stretch from stellar astrophysics all the way to cosmology. And that's why Caffau's star continues to fascinate astronomers. It isn't just a problem, it's a clue. Every alternative explanation, even the ones that fall short, is a step toward uncovering the hidden rules that govern the birth of the first stars. When scientists began to study Caffau's star in detail, one question loomed above all others. Could this faint, quiet star be a relic from the dawn of the universe? In other words, is it possible that we are looking at one of the oldest surviving stars in existence, a direct witness to the time when the cosmos was young, raw, and newly lit after the darkness of the Big Bang? The idea isn't far-fetched. Caffau's star has all the hallmarks of a primordial survivor. Its composition is almost pure hydrogen and helium, with virtually no metals, a signature that places it very close to the first stages of cosmic evolution. Unlike the Sun, which contains elements forged in countless generations of earlier stars, Caffau's star is practically pristine. It is as if it were plucked out of a universe only recently born, frozen in time, and left to shine faintly for over 13 billion years. To understand why this is such a big deal, we need to recall how stars typically evolve. The first stars, the so-called population 3 stars, were expected to be massive and short-lived. They would have burned their nuclear fuel furiously, exploding as supernovae within just a few million years. Their deaths seeded the universe with heavier elements, enabling the formation of later generations of stars, planets, and eventually life. According to theory, no small, long-lived stars could have formed in that early metal-free universe, because the gas clouds couldn't cool enough to fragment into such small clumps. And yet, Caffau's star seems to be exactly that, a small, low-mass star with a nearly primordial composition. This opens the door to the tantalizing possibility that it is a true relic star. If it formed before the universe was significantly enriched with metals, then it could date back to an epoch not long after the Big Bang itself. Imagine what that means. While galaxies were just beginning to assemble, while black holes were still in their infancy, while cosmic structures were first taking shape, this star was already burning hydrogen in its core. And billions of years later, while countless stars have lived and died, while entire galaxies have merged and evolved, Caffau's star still endures. Its very survival is tied to its mass. Massive stars live fast and die young, but small stars, the ones with a fraction of the Sun's mass, sip their nuclear fuel slowly. They can burn for tens or even hundreds of billions of years, far outlasting larger stars. Caffau's star is one of these small, dim dwarfs. Its low mass allows it to endure from ancient times until today, a cosmic candle burning at an incredibly slow pace. In fact, it will probably still exist long after the Sun has swelled into a red giant and died. But is it truly a relic from the first generation? Or is it a slightly younger star, born from gas that was almost pristine but already lightly enriched by the deaths of massive stars? This is where things get tricky. The absence of metals in Caffau's star strongly suggests that it formed from gas unpolluted by earlier supernovae. Yet astronomers can't entirely rule out that it might belong to an early population 2 generation, stars that formed after the very first, but still with incredibly low metallicity. If that's the case, then it may not be the very first of the first, but still one of the earliest survivors we can observe today. Think of it this way: if the universe is a book, with each generation of stars representing a new chapter, then most stars we see today are from chapters far into the story. The Sun, for instance, is a character introduced well into the cosmic novel. But Caffau's star? It might be from page 1 or 2. It carries within its light the memory of the beginning of the universe's grand narrative. Astronomers refer to such objects as stellar fossils. Just as paleontologists dig up ancient bones to understand Earth's deep past, astrophysicists study ancient stars to reconstruct the conditions of the early cosmos. And unlike bones, which decay over millions of years, these stellar fossils remain burning in the sky, their chemical composition preserved for billions of years. Every photon emitted by Caffau's star is a message from the ancient universe, whispering secrets about what the cosmos was like in its infancy. If Caffau's star truly is a relic, its implications are profound. It suggests that the early universe may have been capable of producing small, long-lived stars under certain conditions, even if those conditions were rare. That means the cosmic history we've constructed, where the first stars were exclusively massive, short-lived behemoths, may be oversimplified. Perhaps alongside the giants, a few tiny survivors were born, hidden like needles in the cosmic haystack. And now, billions of years later, we are finally finding them. Some astronomers even speculate that stars like Caffau's may be more common than we think, scattered throughout the halo of the Milky Way, waiting to be discovered. If true, it would mean the universe has been keeping its oldest relics in plain sight, faint but enduring, long after most of their peers have perished. But even if Caffau's star is not the very first generation, its age is still staggering. Estimates suggest it could be over 13 billion years old, placing its birth just a few 100 million years after the Big Bang. That alone makes it one of the oldest stars ever identified, a near contemporary of the first galaxies themselves. The possibility that we are seeing something that ancient, still alive, is humbling. It's as though we stumbled upon a living creature that walked the Earth with the very first organisms, surviving against all odds into the present day. So, is Caffau's star a relic? Most astronomers lean toward yes, at least in the sense that it is a fossil of the early universe, even if not the absolute first generation. Its chemical purity, its low mass, and its survival all point toward it being one of the universe's primordial survivors. And as long as it continues to shine, it will remain a direct link to an epoch otherwise hidden in darkness, a silent witness to the very birth of stars themselves. When we talk about the age of Caffau's star, we are really trying to place it within the vast timeline of cosmic history. The universe itself is about 13.8 billion years old, and any star suspected of being a relic of the earliest epochs must have formed very soon after the Big Bang. The question is, how do astronomers determine whether Caffau's star might be 13 billion years old or more, and what clues in its composition and behavior allow us to estimate such staggering ages? First, let's break down the cosmic clock. After the Big Bang, the universe expanded and cooled rapidly. Within the first 3 minutes, Big Bang nucleosynthesis created the lightest elements, hydrogen, helium, and a trace of lithium. But after that, the cosmos entered a long dark age. For nearly 400 million years, there were no stars at all, just vast clouds of cooling gas. Eventually, under the pull of gravity, these gas clouds collapsed to form the first stars, igniting the cosmic dawn. Those first stars, the population 3 stars, lived short lives, exploding after only a few million years and enriching the cosmos with heavier elements. By the time the universe was 1 billion years old, galaxies had begun to assemble, and the first generations of long-lived stars were being born. Now, here's where Caffau's star comes into the picture. Its extraordinarily low metallicity, meaning its near-complete absence of heavier elements, places it close to that early epoch. The less metal a star contains, the earlier it must have formed, because every subsequent generation of stars pollutes the universe with more metals. By the time stars like our Sun formed, about 4.6 billion years ago, the interstellar medium was already rich in carbon, oxygen, iron, and many other elements. Caffau's star, by contrast, has almost none of these. That means it must have formed when the universe was still in its youth, before the cycle of star death and rebirth had time to enrich the cosmos substantially. But how old is youth in cosmic terms? Let's consider the evidence. The Sun, for comparison, is a population 1 star, about 4.6 billion years old, with high metallicity. Most stars in the Milky Way's disk are in this category, relatively young and metal-rich. The halo of the Milky Way, however, is filled with ancient, metal-poor stars, belonging to population 2. These halo stars often have ages between 11 and 13 billion years. Caffau's star resides in this halo, far from the galaxy's bustling, metal-rich disk. Its location alone is a clue that it belongs to one of the earliest stellar populations. Astronomers estimate the age of such stars not by counting years directly but by modeling stellar evolution. Stars like Caffau's burn their hydrogen fuel so slowly that their lifespans can extend longer than the current age of the universe. So, if we find one with a primitive composition and low mass, we can infer that it has been shining steadily since it first formed billions of years ago. Models suggest that Caffau's star could have formed over 13 billion years ago, perhaps only a few 100 million years after the Big Bang. Another way to constrain the age is by comparing it to the oldest known globular clusters, dense groups of ancient stars bound together by gravity. Many globular clusters in the Milky Way have ages estimated at 12 to 13 billion years. These clusters are thought to have formed very early in the galaxy's history, and the stars within them show similarly low metallicities. Caffau's star, however, is even more extreme in its lack of metals, suggesting it could be as old as, or even older than, the stars in those clusters. Yet there's a deeper layer to this. The most astonishing aspect of Caffau's star is not just that it's old, but that it could have survived so long while being formed under conditions we thought were impossible. Its chemical fingerprint, the near absence of lithium and heavier elements, indicates that it may have formed from a gas cloud almost untouched by earlier supernovae. That would mean it is a survivor from a time when the universe was still nearly pristine, possibly one of the very first small stars to form after the population 3 giants exploded. If that's true, then its age is not just over 13 billion years, but potentially close to the maximum age allowed by the universe itself. The concept is almost dizzying. Imagine a star that began shining when the Milky Way itself did not yet exist as a coherent galaxy, when the first large-scale structures were still assembling from smaller fragments. Caffau's star may have witnessed the cosmic dawn firsthand. And yet, despite the billions of years that have passed, the rise and death of countless stars, the birth of planets, the merging of galaxies, this faint star has endured, undisturbed, in the quiet halo of our galaxy. What makes this even more incredible is that we may be seeing the star not just as an old object but as a living fossil. Unlike galaxies or clusters, which have evolved and changed dramatically over billions of years, a small star like Caffau's changes little over time. It is essentially the same now as it was billions of years ago, burning hydrogen slowly in its core, radiating faintly into the cosmos. In this sense, looking at Caffau's star is like having a time machine. It gives us a direct glimpse into the chemistry and physics of the early universe. The age estimates of over 13 billion years don't come with absolute certainty. Astrophysics is rarely that exact when dealing with such extreme timescales. But even the most conservative estimates place the star's formation within the first billion years of cosmic history. That makes it not only older than the Sun by more than twice the Sun's age but also nearly as old as the universe itself. So when astronomers say that Caffau's star might be over 13 billion years old, what they really mean is that it formed during the childhood of the universe and has managed to survive all the way to the present. It is, in every sense of the word, ancient, a star whose birth is closer in time to the Big Bang than to us. When astronomers talk about stars with extremely low metallicity, Caffau's star is never alone in the conversation. Over the past few decades, several stellar fossils have been discovered that challenge our ideas of how stars formed in the early universe. These stars are often labeled EMP stars, extremely metal poor, or, in more extreme cases, UMP stars, ultra metal poor, and HMP stars, hyper metal poor. They are some of the most primitive stars we've ever found, scattered mostly in the halo of the Milky Way, orbiting far from the bustling galactic disk. Each of these ancient stars tells its own story about the early cosmos, but when compared to them, Caffau's star still manages to stand out as something even stranger. Let's look at a few examples first, because understanding what other low metallicity stars look like helps us appreciate how unusual Caffau's star really is. One of the most famous discoveries before Caffau's star was He 0107-5240, found in 2001. This star was hailed as one of the most metal-poor stars ever detected, with an iron abundance about 1/200,000th of the Sun's. In astronomical terms, that's almost nothing. But there was a twist. Despite having extremely low iron, He 0107-5240 showed very high abundances of carbon, nitrogen, and oxygen. That's important, because these elements act as coolants in gas clouds. Their presence allows the gas to fragment more easily, enabling the formation of small stars rather than only massive ones. So while He 0107-5240 was an astonishing find, it could still fit within theoretical models, because astronomers could argue that carbon enrichment was the key that made its formation possible. Another star, He 1327-2326, discovered in 2005, pushed the metallicity envelope even further. It had an iron abundance even lower than He 0107-5240, making it one of the most chemically primitive stars ever found. Like the previous star, though, it also displayed relatively high levels of carbon. Once again, the presence of carbon acted as a loophole in theory. Maybe such stars could form if their parent gas clouds were seeded with carbon by the deaths of earlier massive stars. The carbon provided a cooling pathway, allowing low-mass stars to form and survive into the present day. Then came SDSS J102915+172927, discovered in 2014, which stunned astronomers with iron levels lower than any star previously measured, essentially undetectable, less than 1/10,000,000th of the Sun's iron abundance. But once again, this star showed high levels of carbon. The pattern was clear. The most metal-poor stars we had found up until that point all had a compensating enrichment in carbon. The explanation worked. Carbon acted as the cooling agent that theory demanded. And this is where Caffau's star throws the curveball. Unlike those other extremely metal-poor stars, it does not have high levels of carbon. In fact, its carbon, nitrogen, and oxygen levels are astonishingly low, so low that they are barely detectable at all. Even lithium, predicted to exist in small amounts from Big Bang nucleosynthesis, is missing. That makes Caffau's star fundamentally different from the others. To put it another way, stars like He 0107-5240 and SDSS J102915+172927 are weird. Yes, but they can be explained by invoking carbon as the cooling agent. They bend the rules but don't quite break them. Caffau's star, however, takes the rulebook and tears it in half. According to theory, it shouldn't exist at all. Without metals like carbon or oxygen to cool its parent gas cloud, there should have been no way for such a small, low-mass star to form. The gas should have stayed too hot, collapsing only into very massive stars that lived short lives. Yet here we are, staring at a small, dim, ancient star that clearly did form, and that has survived for over 13 billion years. Astronomers often highlight this comparison because it underscores just how puzzling Caffau's star is. The others, strange as they are, still provide theoretical footholds. But Caffau's star leaves us dangling over a gap in our understanding. If it formed without carbon, oxygen, or detectable lithium, what exactly allowed its gas cloud to fragment and collapse into a low-mass star? That's a mystery that has yet to be fully resolved. Another important distinction is the sheer rarity of stars like this. Metal-poor stars are difficult to find because they are faint and often reside in the outskirts of galaxies. Even among these rare objects, the combination of extremely low metallicity and the absence of carbon enrichment makes Caffau's star practically unique. It's like searching through a collection of fossils and suddenly finding one that doesn't fit any known evolutionary tree, a creature that seems to have bypassed the rules of biology altogether. And then there's the matter of lithium. Most extremely metal-poor stars show at least some lithium, consistent with Big Bang predictions. But Caffau's star does not. This is another way it stands apart from its peers. Not only is it more chemically pristine than nearly all of them, but it also lacks even the light elements that cosmology tells us should have been there from the beginning. The comparison becomes even more striking when we remember that these stars are not scattered randomly across the sky. They live in the halo of the Milky Way, which itself is ancient and full of relics from the galaxy's earliest history. Yet even in that ancient environment, where low metallicity stars are relatively common, Caffau star remains an outlier. It's not just another old star, it's one that defies the patterns astronomers have come to rely on when interpreting the first phases of cosmic evolution. So when we line them up, He 0107 to 5240, He 1327 to 2326, SDSS J102915+172927, and Caffau star, we see a spectrum of ancient survivors, each extraordinary in its own way. But Caffau star is the oddest of the bunch, because it breaks the trend. It's the one that forces scientists to admit, our models might not just be incomplete, they might be missing something fundamental. That's why, in comparison with other stars, Caffau star is even stranger. It doesn't just test the boundaries of theory, it steps completely outside them. It's a quiet reminder that the universe does not always obey the neat categories we create. Sometimes, it throws us an anomaly that refuses to fit, and in those moments, science is pushed forward, because we're forced to look deeper and rethink what we thought we knew. The discovery of Caffau star brings us face to face with one of the most profound questions in modern cosmology. What does this strange little star actually mean for the Big Bang theory itself? After all, the Big Bang is not just a casual idea. It is the foundational framework of modern astrophysics, the story we tell about the origin and evolution of the universe. From the cosmic microwave background to the distribution of galaxies, from the abundance of light elements to the expansion of space itself, every piece of evidence we've gathered over the past century points toward the Big Bang as the moment when our universe began. So when we encounter an object like Caffau star, which seems to defy the predictions of that framework, it's natural to ask, does this discovery invalidate the Big Bang, or does it merely highlight the gaps in our current understanding of the details? To address this, we first need to revisit what the Big Bang actually claims. The Big Bang theory explains that the universe began in a hot, dense state and expanded over billions of years into what we see today. It predicts that the early universe produced hydrogen, helium, and a small but measurable amount of lithium during a process called Big Bang nucleosynthesis. It also tells us that the very first stars should have been massive, short-lived, and devoid of metals, the so-called population 3 stars. Later generations, formed after the deaths of those first giants, should have incorporated small amounts of carbon, oxygen, and other heavy elements. From that perspective, the existence of Caffau star raises several red flags. It is a small, long-lived star that seems to have formed from nearly pristine gas. It shows almost no carbon, no oxygen, and puzzlingly, no lithium. According to the neat story outlined by Big Bang cosmology and subsequent models of star formation, such a star should not exist. But here's the key point: challenging the details of star formation is not the same thing as disproving the Big Bang itself. The Big Bang explains the broad strokes, the origin of the universe, the initial chemical composition, the expansion of space, and the large-scale structure we observe. Caffau's star doesn't overturn those cornerstones. Instead, it calls into question the specific processes by which the first low-mass stars formed. Think of it this way: the Big Bang theory gives us the stage, the setting, and the opening act of the cosmic play. What stars like Caffau's do is force us to reconsider the script we've written for how the first characters entered and interacted. The existence of this star doesn't mean the stage isn't real. It means the story is more complicated than we assumed. This distinction is crucial because science thrives not by throwing out entire frameworks whenever anomalies appear, but by refining and expanding them. Take the example of the cosmic microwave background. When it was first detected, it didn't fit perfectly with early versions of the Big Bang model. Instead of abandoning the theory, scientists adjusted their models, incorporating new physics and gaining a deeper understanding of the early universe. A similar process is happening now with stars like Caffau's. So, what specifically does Caffau star tell us about the Big Bang? For one, it highlights a potential gap in our understanding of Big Bang nucleosynthesis. Lithium, in particular, has long been a sticking point. The so-called cosmological lithium problem refers to the fact that the observed abundance of lithium in old stars doesn't match theoretical predictions. Caffau star takes this problem to an extreme, with virtually no detectable lithium at all. Does that mean our models of element production in the early universe need tweaking? Possibly. It also challenges the cooling problem in star formation. If metals like carbon and oxygen were required for small stars to form, then how did Caffau star come into existence without them? Perhaps there are alternative cooling mechanisms we haven't fully accounted for, such as the role of dust or molecular hydrogen. Or maybe new, exotic physics is at play. Either way, the existence of this star suggests that our models of early star formation, which are built on top of Big Bang cosmology, are incomplete. Another layer to this is philosophical. When people hear this star breaks the Big Bang, it sounds as though the entire theory of cosmic origins is on the chopping block. But in science, anomalies are not usually theory killers, they're opportunities. In fact, anomalies are the engines of progress. When Newtonian physics couldn't explain the orbit of Mercury, scientists didn't abandon physics altogether, they developed general relativity. When classical physics couldn't explain atomic spectra, we got quantum mechanics. Caffau star may not destroy the Big Bang. Instead, it might be pointing us toward the next refinement of our cosmic story. This brings us to an even more fascinating possibility. Could it be that stars like Caffau's are not just weird outliers, but keys to unlocking new physics? If we discover more such stars, and if their properties consistently defy current models, it may force us to rethink not just how the first stars formed, but also aspects of the Big Bang itself. Maybe Big Bang nucleosynthesis was more complex than we think. Maybe there are unknown processes that altered the composition of the earliest gas clouds. Or maybe dark matter, which makes up most of the universe's mass but remains invisible, played a more direct role in the formation of the earliest low-mass stars. For now, the safest conclusion is this: Caffau star does not prove the Big Bang wrong. What it does is expose the limitations of our current models of early star formation and element distribution. It reminds us that our theories, no matter how elegant, are only approximations of reality, and reality always has the final word. In that sense, Caffau star is not a threat to the Big Bang. It is a gift. It is a messenger from the earliest epoch of the universe, whispering to us that the story is not yet fully written, that there are still mysteries waiting to be solved. It doesn't tell us to abandon the Big Bang. It tells us to dig deeper, to refine our models, to remain humble in the face of a cosmos that is always more complex than we imagine. The story of Caffau star is not just about theory and cosmology, it's also about the immense difficulty of even finding such an object in the first place. Ancient stars like this are not the blazing giants of the Milky Way that draw the eye. They are the quiet, faint survivors that lurk on the edges of detectability, buried in the noise of the cosmos, and hidden among the countless billions of other stars in our galaxy. To grasp the significance of its discovery, we need to understand just how difficult it is to observe faint, ancient stars like Caffau's, and why the limits of our observational technology play such a crucial role in our ability to uncover the secrets of the early universe. First, let's consider brightness. Stars like Caffau's are low-mass stars, meaning they burn their hydrogen fuel slowly and gently. This is why they can live for billions of years, outlasting the more massive stars that exploded long ago. But longevity comes at a cost. They are intrinsically faint. Caffau star, for example, is a dwarf star with a luminosity far, far dimmer than that of the Sun. Even though it lies within our own Milky Way galaxy, only about 4,000 light-years away, it appears as nothing more than a tiny pinprick of light in the sky, invisible to the naked eye, and requiring specialized instruments to study in detail. This faintness is compounded by the fact that ancient stars like this often reside in the halo of the Milky Way, a vast, sparsely populated region surrounding the galaxy. Unlike the bright, dense galactic disk where young stars thrive, the halo is a dim, diffuse sphere of old stars and dark matter. Finding an ancient metal-poor star in the halo is like trying to spot a single firefly in the middle of a distant forest at night. They are simply overwhelmed by the backdrop of brighter, younger stars that dominate the galaxy's main body. But brightness isn't the only challenge. To determine whether a star is truly ancient and metal-poor, astronomers need to perform spectroscopy, the science of splitting starlight into its component wavelengths and analyzing the resulting spectrum. A spectrum is like a barcode, revealing which elements are present in the star's atmosphere. Iron lines, carbon features, oxygen signatures, and lithium absorption, all of these appear, if they exist, as delicate fingerprints etched in the light. For bright stars, spectroscopy is relatively straightforward. But for faint stars like Caffau's, obtaining a high-quality spectrum is excruciatingly difficult. Long exposure times are required, often using the world's most powerful telescopes, such as the Very Large Telescope, VLT, in Chile, which was instrumental in Caffau's discovery. Even then, the data can be noisy, and distinguishing between a true absence of metals and an absence caused by the limits of detection is a painstaking process. Adding to the complexity is the fact that ancient stars don't wear signs saying, "I'm primordial." They look, at first glance, like any other faint star in the sky. It is only by trawling through vast surveys of stars, carefully selecting candidates that might be metal poor, and then following up with detailed spectroscopy, that astronomers can sift out the rare fossils from the crowd. Caffau's star was identified through the Sloan Digital Sky Survey, SDSS, a massive project that has catalogued millions of celestial objects. Even within that ocean of data, it was just one faint dot with unusual characteristics. This means that the stars we have already discovered, as rare as they are, may represent only a tiny fraction of what is really out there. The faintest, most ancient stars could still be hiding beyond the sensitivity of our current instruments. Our telescopes are powerful, but they have limits. As we look further out, stars become not only dimmer but also harder to distinguish from galaxies or background noise. Even within the Milky Way, faint stars can be drowned out by interstellar dust that blocks and scatters their light. It is humbling to realize that the universe may be filled with many more Caffau stars, perhaps thousands or millions of them, and we simply cannot see them yet. Our current catalogue of extremely metal-poor stars may be only the tip of the iceberg. This limitation means that the story of early star formation is incomplete not only because our theories are imperfect, but also because our observations are still catching up. And this is where new technology becomes critical. Next-generation observatories, such as the James Webb Space Telescope, JWST, and the upcoming Extremely Large Telescope, ELT, promise to extend our reach, allowing us to probe faint stars with unprecedented detail. With these instruments, astronomers hope to uncover more stellar fossils, perhaps even stars stranger than Caffau's. If we can build a larger sample size, we may finally be able to answer whether Caffau's star is a bizarre one-off anomaly or part of a hidden population of ancient survivors. Another layer to the difficulty is time itself. These stars are old, but not immortal. Over the past 13 billion years, countless other low metallicity stars may have already burned out, exploded, or been destroyed through interactions with other stars and black holes. That means the surviving examples are even rarer than they would have been in the early universe. We are searching not just for needles in haystacks, but for needles that have survived for nearly the entire lifetime of the universe. The difficulty of observing Caffau's star reminds us of a sobering truth. Our picture of the cosmos is constrained not only by the accuracy of our theories but by the limits of our vision. We can only interpret what we are able to see, and sometimes what we cannot yet see is the most important of all. Stars like Caffau's may be scattered across the galaxy, silently holding secrets about the birth of the cosmos, waiting for us to develop the tools and methods to uncover them. This limitation also tempers our conclusions. When we say Caffau's star breaks the rules, we must also admit that our view is incomplete. Perhaps the discovery of dozens more stars like it would transform it from an anomaly into a pattern. Or perhaps we'll find that it truly is unique, a singular oddity in the universe's history. But until we overcome the challenges of observing faint, ancient stars, we can't know for sure. And so, the limits of observation become part of the mystery themselves. The faintness, the distance, the difficulty of spectroscopy, all of these are not just obstacles but also motivators. They push astronomers to build better instruments, refine their methods, and explore deeper into the night sky. Every technological leap brings us closer to pulling back the veil on the early universe. And in that sense, the struggle to observe Caffau's star and its peers is not a weakness of science, but its strength, a sign that the quest for knowledge never stops at the first difficulty, but presses forward into the unknown. When Caffau's star was first announced in 2011, the reaction across the astronomical community was one of shock and cautious fascination. On the one hand, the discovery represented a spectacular triumph of observational astronomy. An international team, led by Elisabetta Caffau, had pushed the Very Large Telescope in Chile to its limits and pulled a treasure out of the cosmic haystack, a star so ancient and metal-poor that it immediately demanded global attention. On the other hand, the data seemed to strike at the heart of long-held theoretical assumptions about how stars form. This duality, the exhilaration of discovery and the unease of contradiction, defined the community's response. To appreciate why astronomers reacted the way they did, you need to understand the culture of modern science. Cosmology and astrophysics are built on deeply interconnected models. Big Bang nucleosynthesis, cosmic microwave background measurements, stellar evolution, and galaxy formation all mesh together into a tapestry that explains the universe's history. When a new observation threatens to unravel one piece of that tapestry, the first instinct is not to throw the whole thing out, but to ask, where can the model be refined, expanded, or corrected? That's exactly how most astronomers responded to Caffau's star. They were surprised, even stunned, but not ready to abandon the Big Bang. The Big Bang model itself had too much going for it, too much independent evidence in its favor, to be discarded because of a single anomalous star. The cosmic microwave background, the abundance of light elements, the redshift of galaxies, all of these pillars remained standing. Instead, the focus quickly shifted to asking whether the contradiction lay not with the Big Bang itself, but with our models of early star formation. It's worth pausing here to note just how bold the idea of the Big Bang had once been. For much of the 20th century, it was a controversial, radical hypothesis. Only with decades of accumulating evidence did it become the dominant cosmological model. Scientists did not embrace it lightly, nor would they abandon it lightly. By the time Caffau's star appeared, the Big Bang framework was so robust that any potential threat had to be weighed against the sheer mountain of supporting evidence. So when astronomers were confronted with this metal-poor anomaly, the consensus reaction was something like, "This is extraordinary. It challenges us." But the solution is probably in the details of star formation physics, not in rejecting the Big Bang itself. This measured response was reflected in the scientific papers that followed. Rather than framing the star as evidence against the Big Bang, researchers explored more nuanced interpretations. They asked questions like, could dust have been more important in cooling than we realized? Could molecular hydrogen have played a larger role? Were there previously unconsidered pathways for fragmentation in metal-poor gas clouds? In other words, the anomaly sparked theoretical creativity, not panic. At the same time, the discovery of Caffau's star was embraced with genuine excitement. For many astronomers, anomalies are not embarrassments but opportunities. They represent cracks in the wall of our understanding through which new light can enter. The fact that a star could defy so many expectations was not seen as a failure of astrophysics, but as a chance to probe deeper into the processes that governed the early universe. Of course, not everyone reacted with equal calm. Some voices, particularly outside the core astrophysics community, were quick to jump on headlines like "This star breaks the Big Bang theory." Such claims circulated in popular science media, sometimes with exaggerated tones suggesting that the entire cosmological model was in jeopardy. Within the scientific community, however, the reaction was more restrained. Most specialists emphasized that while Caffau's star was extraordinary, one object alone was not enough to overturn decades of cosmological evidence. They stressed that science advances by accumulating data, and that until more stars like it were found, the anomaly should be treated as a puzzle, not a paradigm shift. That doesn't mean the community dismissed it. On the contrary, the discovery lit a fire under efforts to search for more extremely metal-poor stars. The reasoning was straightforward. If Caffau's star were truly unique, then perhaps it was just an odd outlier, a strange product of unusual conditions. But if more like it could be found, the case for revising star formation models would become undeniable. The reaction, therefore, was to look harder, build better surveys, and develop sharper tools. The star also became a touchstone in conference discussions and debates. Astrophysicists would point to it as a reminder that their models are only approximations of reality, not reality itself. Theories are powerful, but the universe always has the final word. Caffau's star was, in a sense, the cosmos tapping scientists on the shoulder and saying, "Not so fast. There's more to this story." This tension between surprise and caution, excitement and restraint, captures the essence of how the scientific community works. Scientists are trained to avoid overreaction. They are also trained to follow anomalies wherever they lead. In the case of Caffau's star, the reaction revealed both sides of that training. The star didn't cause anyone to abandon the Big Bang. But it did cause everyone to ask better, harder questions about the details of how stars formed in the universe's infancy. And perhaps most importantly, the reaction showed humility. Despite all of humanity's advances in physics, telescopes, and computational models, here was a faint little star, almost invisible against the background of space, reminding us that nature still holds mysteries we cannot yet explain. That humility, the willingness to be surprised, to admit what we don't know, and to pursue the answers with vigor, is what keeps science alive. The discovery of Caffau's star was already fascinating enough when framed as a challenge to our models of star formation. But for some astronomers and physicists, the implications stretch even further. What if the anomaly isn't just about gas cooling, dust, or star formation mechanics? What if the existence of a star like this hints at undiscovered physics, processes or principles in the early universe that our current theories simply don't capture? This idea can sound dramatic, even speculative, but history shows that moments like this often open the door to new physics. Consider how the ultraviolet catastrophe of the 19th century, a small anomaly in black-body radiation, forced the birth of quantum mechanics. Or how the precession of Mercury's orbit, just a tiny mismatch with Newtonian predictions, paved the way for Einstein's general relativity. Sometimes, the universe whispers its secrets not through giant contradictions, but through quiet, persistent anomalies that force us to reimagine the rules. Caffau's star could be one of those whispers. The first place scientists look for undiscovered physics is in the details of Big Bang nucleosynthesis, BBN. This is the theory that describes how hydrogen, helium, and trace amounts of lithium were formed in the first few minutes after the Big Bang. The problem with Caffau's star is not just its extreme metal-poor nature, but also its lack of detectable lithium. According to standard BBN, there should have been a specific baseline of lithium in the primordial universe. Yet, not only does Caffau's star lack it, this lithium problem has cropped up before, with other old stars showing less lithium than expected. If this lithium discrepancy is not just an observational error or a quirk of stellar evolution, it might hint that our understanding of the early universe's chemistry is incomplete. Perhaps unknown nuclear reactions occurred in those first minutes. Or maybe some exotic particle physics process, such as the decay of dark matter particles or interactions involving neutrinos, altered the balance of light elements in ways we haven't yet modeled. Another line of thought involves the possibility that fundamental constants of nature may not have been constant in the earliest epochs. If the strength of the strong nuclear force, or the fine structure constant, or even the mass of the electron was slightly different in the early universe, nucleosynthesis could have unfolded differently. That would ripple forward into the chemistry of stars, potentially explaining why stars like Caffau's don't fit our predictions. It's a bold idea, but one that cosmologists keep in mind when faced with unexplained data. There's also the possibility of alternative cooling mechanisms tied to undiscovered physics. For example, some researchers have suggested that exotic particles, perhaps related to dark matter, could have provided a pathway for primordial gas clouds to shed energy and collapse into small stars, even without metals. If dark matter, which we know makes up most of the universe's matter content, interacts in ways beyond just gravity, it could influence star formation in subtle but profound ways. This line of speculation connects Caffau's star directly to one of the biggest mysteries in physics, the true nature of dark matter. Then there are theories involving population 3 remnants. What if some of the first stars were not as massive and short-lived as we thought, but some managed to survive in a way we haven't accounted for? This would force us to rethink stellar physics under extreme, metal-free conditions. Could unknown quantum effects in the cores of primordial stars have allowed them to stabilize longer than expected? Could our equations for how convection, opacity, or fusion rates behave in metal-free plasma be missing something? Each possibility opens the door to new physics waiting to be discovered. It's important to note that most astronomers remain cautious here. The standard practice in science is to exhaust conventional explanations first. After all, the history of astronomy is filled with anomalies that later turned out to be solvable without rewriting the laws of physics. But the possibility remains, lingering at the edges of discussions about Caffau's star. Maybe this faint star, sitting quietly in Leo, is a messenger from the dawn of time, carrying with it evidence of physics we haven't yet discovered. And that possibility is what excites theorists most. Because if new physics is required to explain stars like Caffau's, the implications go far beyond one star. It would mean the early universe behaved differently than we think. It would mean that the story written in the cosmic microwave background, in the distribution of galaxies, in the evolution of stars, might need to be expanded or reframed. And it would mean that we stand on the brink of a deeper understanding of reality itself. This is why scientists didn't dismiss Caffau's star as just a curiosity. Even if the anomaly eventually finds an explanation within the boundaries of existing theory, the possibility that it hints at new physics keeps researchers engaged. In the grand sweep of science, anomalies are the fuel that drive progress. They are the questions that cannot yet be answered, the loose threads in the fabric of knowledge that invite us to pull, to tug, to see what unravels. So while most astronomers say the Big Bang itself is safe, they also admit that Caffau's star might be pointing to something more subtle but no less profound. It might be telling us that there's a layer of physics underneath our current models, something woven into the first seconds of cosmic history, waiting for us to uncover. And if that's true, then this little star, faint and unassuming in the night sky, could be a key that unlocks one of the deepest secrets of the universe. The discovery of Caffau's star didn't end with the moment Elisabetta Caffau and her colleagues announced their results in 2011. In many ways, that was just the beginning. Almost immediately, the astronomical community realized that this single star raised more questions than it answered. And so began a new chapter, the hunt for more stars like it. Because in science, one anomaly is tantalizing but never definitive. If we can find others, patterns emerge, theories can be tested, and the mystery deepens into something we can start to understand. The search for ultrametal-poor stars has always been difficult. These stars are faint, ancient, and often hidden among the far brighter and more numerous stars in our galaxy. They don't announce themselves with flashy colors or strong signals. Instead, astronomers must sift through enormous catalogues of stars, painstakingly measuring their spectra to look for the subtle fingerprints of metals, or in this case, the near absence of them. Caffau's star, with its exceptionally low metallicity, was like finding a needle in a haystack the size of the Milky Way. That's why astronomers quickly realized that systematic surveys would be essential. Random luck had given us one example, but to truly test the theories of early star formation, we needed many more. Enter large-scale sky surveys like the Sloan Digital Sky Survey, SDSS, which had already been instrumental in identifying Caffau's star. SDSS had catalogued millions of stars, galaxies, and quasars, providing a vast database for astronomers to comb through. But identifying candidates required clever filtering, searching for stars whose spectra hinted at extraordinarily low metal content, then following up with more detailed observations using the most powerful telescopes available. After 2011, the hunt intensified. Teams turned to the Very Large Telescope, VLT, in Chile, where Caffau's star was originally confirmed, and other instruments like the Keck Observatory in Hawaii and the Subaru telescope. These facilities were capable of capturing the high-resolution spectra needed to detect or rule out tiny amounts of elements like iron, carbon, and oxygen. Each observation was like interrogating the light from a star, asking it to reveal its chemical history. But even these massive telescopes could only do so much, given the faintness of the targets. That's why astronomers began to plan for next-generation tools. Projects like the European Extremely Large Telescope, EELT, and the 30-meter telescope, TMT, are designed with exactly this kind of research in mind. Their immense mirrors will collect more light, allowing us to probe fainter, older stars at greater distances, perhaps even beyond the Milky Way. The hope is that with these instruments, the search for metal-poor stars won't just uncover a handful of anomalies, but a whole new population waiting to be studied. Meanwhile, new surveys on Earth and in space are adding to the arsenal. The Gaia mission, launched by the European Space Agency, has been mapping the positions, motions, and brightness of over 1 billion stars in our galaxy. While Gaia doesn't directly measure metallicity with high precision, it provides an incredibly detailed roadmap that allows astronomers to identify likely candidates for follow-up. For instance, by tracking the motions of ancient stars that orbit in the Milky Way's halo, the outer, spherical region of our galaxy, astronomers can zero in on populations most likely to include relics from the early universe. Then there are surveys specifically designed to look for extremely metal-poor stars. Projects like the Pristine Survey at the Canada-France-Hawaii Telescope use narrowband filters tuned to specific wavelengths of light that make metal-poor stars stand out more clearly against the backdrop of normal stars. Other programs, like the SkyMapper Southern Survey in Australia, have dedicated themselves to scanning the skies for faint, ancient stars. These efforts are like dragging finer and finer nets through the cosmic ocean, each time hoping to catch more examples of the elusive class to which Caffau's star belongs. And the results are beginning to show. Since Caffau's discovery, several other stars with extraordinarily low metallicities have been identified. Some are nearly as metal-poor, though none are quite as puzzling in the same way, particularly regarding lithium. Each new find adds a piece to the puzzle. Are stars like Caffau's common but simply hard to detect? Or are they truly rare, with conditions that only occasionally allowed them to form in the early universe? This ongoing hunt has also expanded beyond the Milky Way. Astronomers have started looking into dwarf galaxies, small, faint satellite galaxies that orbit the Milky Way. These galaxies often preserve ancient stars, untouched by the turbulent star formation histories of larger galaxies. By probing these environments, astronomers hope to find stars that formed under conditions even closer to those of the early universe. Dwarf galaxies may hold hidden populations of ultrametal-poor stars, quietly orbiting in the dark, waiting to be found. There's also an important technological angle. Advances in machine learning and data mining are now being applied to the star hunting process. With sky surveys producing billions of data points, no human team could ever sift through them all by hand. But algorithms trained to recognize the spectral signatures of metal-poor stars can scan through catalogs at incredible speed, flagging promising candidates for astronomers to examine more closely. This marriage of astronomy and artificial intelligence has already begun to accelerate the pace of discovery. So, the hunt continues, across the skies, across disciplines, and across time. Each newly discovered ultrametal-poor star is another messenger from the early universe, carrying with it clues about how the first generations of stars lived and died. The more we find, the better we can refine our models, test our predictions, and decide whether anomalies like Caffau's star are quirks of chance or windows into new physics. And here's the thrilling part: we are still at the beginning of this hunt. Our current catalogs are vast, but they represent only a fraction of the stars in our galaxy. With the next generation of telescopes, space missions, and data tools, we may soon uncover dozens, hundreds, or even thousands of stars like Caffau's. If that happens, the mystery will no longer be confined to a single oddball. It will become a new frontier in our understanding of the cosmos. If astronomers were to find just one or two more stars like Caffau's star, the discovery would already be significant, adding weight to the idea that our current models of early star formation are incomplete. But let's take that further. What if surveys reveal not one, not 10, but hundreds or even thousands of these ultrametal-poor, lithium-deficient stars scattered throughout our galaxy and its satellites? That scenario would not just tweak a few details of our theories. It would force us to drastically rewrite the story of cosmic origins. The first and most immediate implication would be that our assumptions about population 3 stars, the very first stars born from hydrogen and helium, were oversimplified or even wrong. Right now, the consensus is that these primordial stars were massive, short-lived, and incapable of surviving into the present. If many long-lived, low-mass, metal-poor stars exist, that would mean the universe had a way of creating small stars from pristine gas much more efficiently than expected. It would suggest that the very first stellar nurseries weren't dominated only by giants that burned out quickly, but also by humble dwarfs that managed to endure for billions of years. This discovery would ripple into our understanding of galactic chemical evolution. Metals, meaning all elements heavier than helium, are produced in stars and spread into space when those stars die. If many small, metal-poor stars survived without contributing much to this recycling process, then the enrichment of the universe with metals would have proceeded more slowly than we currently model. That could change our estimates of how quickly galaxies matured, how soon planets could form, and even how early life could have arisen in the cosmos. It would also profoundly affect how we interpret the timeline of the universe. Right now, astronomers think the earliest galaxies formed when population 3 stars exploded as supernovae, enriching their environments and allowing the next generations of stars to form. But if low-mass, ultra-metal-poor stars were forming alongside those giants and surviving into the present, then the transition from the first stars to the second generation would look very different. Instead of a clean handoff between short-lived giants and younger, metal-bearing stars, we'd see a more complicated picture. A universe where tiny relics of the first epoch quietly lingered while newer stars took shape around them. The lithium problem would also take center stage in this scenario. If many stars showed the same extreme lithium deficiency as Caffau's star, it would no longer be possible to dismiss it as a fluke or an outlier. The case against standard Big Bang nucleosynthesis would become much stronger. Cosmologists would be forced to confront the possibility that either some unknown process destroyed lithium in these stars, or that the primordial lithium abundance was never what we thought it was. In either case, new physics, whether in nuclear reactions, particle interactions, or cosmological conditions, might be required to explain the discrepancy. Finding many more such stars would also force us to revisit the question of cooling mechanisms in star-forming clouds. One of the core assumptions of stellar formation theory is that metals and dust are critical for cooling gas clouds enough to collapse into small stars. If small stars can form in almost metal-free environments, then some other process must be at work. Maybe molecular hydrogen cooling is far more efficient than our simulations suggest. Maybe dust grains formed earlier than we thought. Or maybe, as some speculate, dark matter itself provided an additional cooling channel. Whatever the case, the discovery of many Caffau-like stars would signal that our models of gas physics in the early universe need serious revision. There would also be a profound impact on the search for the first stars and galaxies. Right now, telescopes like the James Webb Space Telescope, JWST, are peering deep into cosmic history to try and catch glimpses of population 3 stars indirectly, through the light of their host galaxies. But if many ultra-metal-poor stars exist in the Milky Way, then relics of the early universe are literally in our backyard. Studying them could give us direct insight into conditions at the dawn of time, without having to rely solely on distant, faint galaxies. That would be a scientific revolution. Instead of looking across billions of light-years, we could look within a few thousand. On a broader scale, such discoveries would also affect the way we think about cosmic habitability. Metals are essential for forming planets, and planets are essential for life as we know it. If metals accumulated more slowly in the universe because so many stars hoarded their primordial gas, then the earliest planets might have formed later than we currently estimate. This could push back the timeline for when life first became possible in the cosmos. In other words, our cosmic calendar might need to be redrawn. Finally, the philosophical impact cannot be ignored. Science is built on models, and those models are built on assumptions. The discovery of Caffau's star already forces us to question some of those assumptions. But if many more like it are found, it won't just be a matter of tweaking the margins, it will be a paradigm shift. It would tell us that the universe is more complex, more surprising, and more resistant to neat categorization than we thought. And history shows that such shifts often lead to profound breakthroughs in our understanding of physics, cosmology, and the nature of reality itself. So, what happens if we find many more stars like Caffau's? The answer is simple but staggering. We would be compelled to rewrite the early chapters of cosmic history. Everything from how stars form, to how galaxies evolve, to how elements are created, would need to be re-examined. The textbooks would change, the models would change, and our picture of the universe's infancy would become richer, stranger, and far more fascinating. When astronomers confront a puzzle as profound as Caffau's star, they often look for answers in unexpected places. And one of the most intriguing possibilities lies in a realm we still barely understand: dark matter. This invisible, mysterious substance makes up about 85% of the matter in the universe, yet it does not emit, absorb, or reflect light. We can't see it directly, but we know it's there because of its gravitational influence on galaxies, galaxy clusters, and the overall structure of the cosmos. For decades, dark matter has been central to cosmology, but what if it also had something to do with the existence of stars like Caffau's? To see how dark matter might fit into the story, let's start with its role in the early universe. After the Big Bang, the cosmos was a hot soup of particles, radiation, and expanding space. Ordinary matter, hydrogen, helium, and traces of lithium, was present, but it interacted strongly with light, meaning it couldn't clump together easily. Dark matter, however, didn't interact with light at all. Instead, it began collapsing under its own gravity, forming invisible scaffolds called dark matter halos. These halos acted like gravitational wells, pulling in gas and providing the seeds for the first galaxies and stars. Without dark matter, structure in the universe might have taken far longer to form, or perhaps not at all. Now, here's where the speculation gets exciting. Some astrophysicists propose that dark matter may have played a direct role in star formation beyond just providing gravitational scaffolding. In the standard picture, gas clouds need to cool before they can collapse into stars. Metals help with this cooling in later generations of stars, but in the primordial universe, with only hydrogen and helium, cooling was inefficient. That's why theory predicts only large, short-lived stars could form. Yet Caffau's star suggests small stars were somehow able to emerge. Could dark matter have provided the missing ingredient? One idea is that interactions between dark matter particles themselves might release energy or help redistribute heat in gas clouds. Some models propose a form of dark matter known as weakly interacting massive particles, WIMPs. If WIMPs can annihilate each other when they collide, they could release energy in the process. This mechanism might have influenced the thermal balance of primordial gas clouds. In fact, some theorists have even speculated about a class of hypothetical objects called dark stars. Dark stars would be powered not by nuclear fusion, like ordinary stars, but by the annihilation of dark matter particles in their cores. They would shine faintly, fueled by invisible matter. If such stars ever existed, they might have altered the conditions for star formation in their neighborhoods, perhaps making it easier for low-mass, metal-free stars to form alongside them. Caffau's star could, in principle, be a relic from such an environment. Though it is not itself a dark star, its existence might hint that dark matter had a hand in shaping its birth. Another possibility involves the role of dark matter gravity. Dark matter halos are thought to dominate the gravitational environment of early galaxies. Their deep gravitational wells could have trapped gas clouds more effectively, giving them extra time to cool and fragment, even with limited metallicity. In this scenario, dark matter doesn't provide a new form of physics within the star, but it does help create the conditions necessary for unusual stars like Caffau's to form in the first place. And then there's the radical idea that dark matter physics itself might be richer than we think. What if dark matter is not a single type of particle, but a whole dark sector with its own forces and interactions? If so, then its role in the early universe could have been far more complex than we currently imagine. Some researchers suggest that interactions within the dark sector could mirror, in some strange way, the interactions of normal matter, meaning there might be dark atoms, dark chemistry, even dark stars that parallel our own. While this remains highly speculative, it opens the door to possibilities where the oddities of stars like Caffau's are not just quirks of ordinary physics, but echoes of a deeper, hidden cosmic layer. Now, it's important to emphasize that these ideas remain speculative. There is no direct evidence yet linking dark matter to the formation of Caffau's star. But scientists take the possibility seriously because anomalies like this demand bold thinking. If ordinary physics struggles to explain how a small, ultra-metal-poor, lithium-deficient star could form, then perhaps the invisible hand of dark matter was at play. If future surveys uncover many more stars like Caffau's, and if these stars seem clustered in particular regions, perhaps near areas where dark matter density is thought to be higher, the case for a dark matter connection would grow stronger. The idea that an invisible substance shaping the galaxies could also leave fingerprints in the birth of the most ancient stars is both haunting and inspiring. It reminds us that we live in a universe where the unseen may be just as important as the seen, and where solving one mystery may require diving headfirst into another. The reason Caffau's star matters, and why astronomers devote so much attention to it despite its faintness, is that it functions like a time capsule from the dawn of the universe. When we study such an object, we are not just looking at another star in our galaxy. We are peering billions of years into the past, into a period of cosmic history otherwise inaccessible to us. It is as if the star is whispering, across eons, this is what the universe was like when it was young. One of the great challenges of modern astronomy is that we cannot directly observe the very first stars. They lived fast and died young, billions of years ago, leaving behind no survivors that we can see today. The only way to learn about them is either to catch their collective signatures in the earliest galaxies through telescopes like JWST, or to find rare relic stars that preserve traces of that epoch. And that is exactly what makes Caffau's star so precious. it appears to be one of those relics. By analyzing the chemical composition of stars like this, astronomers can reconstruct the cosmic genealogy. Every generation of stars leaves behind a chemical fingerprint. The first generation, population 3, seeded the universe with the very first heavy elements when they exploded as supernovae. The second generation, population 2, inherited those elements in trace amounts, and through their own evolution, they enriched the universe further. By studying how much iron, carbon, oxygen, or lithium a star contains, scientists can estimate when it was born and what kind of environment it formed in. Caffau's star, with its extremely low metallicity and almost no detectable lithium, provides a snapshot of conditions that must have existed shortly after the Big Bang, before the universe had become rich with heavy elements. In this way, it is not just an oddball star, it is a direct messenger from the era when the cosmic story was just beginning to unfold. The implications ripple outward. If we can decipher why this star formed and survived, we gain insight into the physics of the early universe. We learn about the processes that cooled primordial gas clouds, about the efficiency of star formation, and about the timing of chemical enrichment. We also confront the limitations of our current models. Caffau's star is not just a curiosity. It is a challenge to theory, a reminder that the universe is more complex than our equations sometimes allow. Furthermore, stars like this offer clues about the origins of galaxies, including our own. The Milky Way did not appear all at once. It grew over time, merging with smaller galaxies and accumulating stars from many sources. Relic stars like Caffau's may have originated in tiny dwarf galaxies that were later swallowed by the Milky Way. If so, studying them also helps us reconstruct the Milky Way's own ancient history, where it came from, how it grew, and how its oldest populations of stars evolved. There is also a deeper, almost philosophical reason why these stars matter. Humanity has always asked where we come from, and the stars hold the answers. Our own existence, the atoms in our bodies, the oxygen we breathe, the iron in our blood, all trace back to processes that began in the first generations of stars. By understanding stars like Caffau's, we are effectively studying the prelude to ourselves. These are the cosmic conditions that eventually made life possible. Finally, the mystery of Caffau's star matters because it forces us to confront the unknown. Science advances not only through confirmations but also through anomalies. When we encounter something that does not fit, we are pushed to expand our theories, to ask new questions, and sometimes to make paradigm shifts. Caffau's star is one of those anomalies. It reminds us that the universe is not fully mapped, that even in our own galaxy there are objects capable of overturning our assumptions. In short, this one faint star matters because it opens a window to the early universe, it challenges our models of cosmic evolution, it connects directly to our own origins, and it embodies the spirit of discovery. It shows that the cosmos is still full of surprises, and that every time we look deeper, we find more reasons to wonder. When people first hear about Caffau's star, it's easy to jump to dramatic conclusions. Does this mean the Big Bang theory is wrong? That's a natural reaction, because the star does seem to fly in the face of some predictions. But science is rarely so black and white. In truth, Caffau's star does not break the Big Bang. Instead, it reframes the conversation and reminds us that the story of the early universe is far more complicated than the simplified version most of us are taught. Think of the Big Bang theory not as a single, rigid law, but as a framework. This framework explains how the universe expanded, cooled, and evolved from an initial hot, dense state. It makes predictions about the relative amounts of hydrogen, helium, and lithium created in the first minutes. It accounts for the cosmic microwave background radiation. It explains the large-scale structure of galaxies we see today. In all these respects, the Big Bang has been enormously successful. The discovery of one strange star does not erase that achievement. Instead, it highlights that within the broader framework, certain details remain unsettled. Here's where Caffau's star becomes crucial. It sits at the boundary between what we think we understand and what we clearly don't. It tells us that the process of star formation in the primordial universe may not have been as straightforward as once assumed. Perhaps gas clouds cooled more efficiently than we thought. Perhaps dust grains, molecular hydrogen, or even exotic processes tied to dark matter played a role. Or maybe our models of lithium production and survival are incomplete. Whatever the explanation, the point is not that the Big Bang is invalid, The point is that the universe is more nuanced than our models currently capture. This is how science grows. Theories are not sacred, they are tools. When a tool fails to explain a phenomenon, we don't throw away the entire toolbox. We sharpen the tool or add a new one. Caffau's star pushes cosmologists and astrophysicists to refine their models of early star formation, to adjust their assumptions about cooling mechanisms, or to reconsider details of Big Bang nucleosynthesis. In this way, the star doesn't destroy the theory, it enriches it. It also serves as a reminder that the cosmos has many layers. The Big Bang sets the initial conditions, but what happens afterward, the collapse of gas, the ignition of fusion, the birth of galaxies, depends on a dizzying interplay of physics, chemistry, and environment. Even a small change in those processes can produce outcomes we didn't predict. Caffau's star may simply be a survivor of one of those unusual outcomes, preserved long enough for us to discover it. And there's another important perspective: anomalies like this are opportunities. Throughout the history of science, anomalies have led to revolutions. The orbit of Mercury didn't fit Newton's equations, which opened the door to Einstein's general relativity. The ultraviolet catastrophe in physics led to the birth of quantum mechanics. Likewise, the oddities of Caffau's star may one day lead to breakthroughs in our understanding of the early universe. If anything, its existence is a gift, a cosmic clue left for us to follow. So rather than saying Caffau's star breaks the Big Bang, it is more accurate to say it deepens the Big Bang story. It tells us that the early universe may have been a richer, more varied place than we once thought. It hints that the conditions for star formation were not uniform, and that in the right circumstances, even stars that shouldn't exist could form. It shows us that our models are powerful, but not perfect. And in science, imperfection is not a weakness, it's a doorway to discovery. As we come full circle in this journey through the mystery of Caffau's star, it's important to pause and reflect on what this faint, ancient object truly represents. At first glance, it is just a dim star in the constellation Leo, invisible to the naked eye, overshadowed by the dazzling brilliance of brighter neighbors. Yet hidden within its spectrum, within the delicate balance of elements it carries, lies a challenge to some of our most deeply held assumptions about the universe. The power of Caffau's star is not in its luminosity, but in its defiance. It doesn't scream across the heavens like a supernova, nor does it tower with the grandeur of a galaxy. Instead, it whispers, almost humbly, a story that unsettles and inspires. It says, "You don't know everything. There is still more to learn." And that whisper carries more weight than the roar of 1,000 ordinary stars, because it points us toward the unknown. In many ways, this star is a mirror. It reflects the state of science itself, incomplete, evolving, forever probing. We humans often like to imagine that we have already uncovered the deepest truths of reality. We write equations, build telescopes, launch satellites, and chart the skies, believing the universe is an open book waiting to be read. But then something like Caffau's star appears, and the pages blur, the ink smudges, and we are reminded that the book is not finished. The story of this star is also a story of humility. Despite decades of research, countless simulations, and generations of astronomers piecing together cosmic history, here stands one small star quietly contradicting parts of the script. It humbles us by proving that the cosmos is not bound by the neat diagrams in our textbooks. It thrives on exceptions, complexities, and mysteries. And yet, that is not discouraging, it's thrilling. Because if the universe were already fully explained, there would be no more frontiers to cross, no new questions to ask, no reason to wonder when we look up at the night sky. The very fact that Caffau's star defies us is proof that the journey of discovery is alive and well. It reassures us that science is not stagnant, but dynamic, growing sharper and deeper with every anomaly we chase. One day, perhaps, we will find the missing piece of the puzzle. Maybe it will come from new simulations, or from the next generation of telescopes uncovering dozens of stars like this one. Maybe it will come from some unforeseen discovery about dark matter, or from an entirely new branch of physics. Whatever the answer, it will expand our vision of the cosmos, just as the discovery of Caffau's star expanded the boundaries of our questions. And so we end with this thought: Caffau's star is not just an astronomical object. It is a symbol. It symbolizes the stubborn mysteries of the universe, the resilience of science to adapt and evolve, and the unending curiosity of humanity. It shows that the cosmos is not a solved equation but an unfolding narrative, one where every star, no matter how faint, can change the story. Caffau's star reminds us that the universe still holds secrets that defy our best theories. And that is the most exciting truth of all. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.